redesigned his.
And the car.
I'm not sure why again. Oh, because he wanted to change the.
I think it's called the Easy Bot Arm.
That's the downside.
Those are mini, the size frame.
Right.
Servos, Bobby King. I forget
Is it
what
Rams?
brand servo.
Not Bob, or is it,
About the highest tip.
You know what I mean by Rams, right?
No. I
0.05
accidentally learned enough. So I've actually got three different servos. This one I already had. I don't remember which one.
That's what I think you used to whenever you grow.
Yeah, I got a ball.
Really appreciate you breaking the
Grabs.
So you're gonna make it 4 axles?
Yeah.
Eventually,
I
I want to put
That's why they get that.
one here from
That's
this
what they
facility.
Yeah,
but
there you go. So it's not, you gotta get it about right.
quite a few.
Yeah, that's a star.
Yeah, like five months.
They go.
It's kind of like a mini Leonardo.
Okay.
The smallest.
And then I was going, there should be an extra.
I didn't bring the power supply today. I just showing up.
It's
Inches per half an inch a second. So it's really too slow, but it'll push 110 pounds.
And there's no point.
But the guy that designed that,
That box
designed kind of like a,
About 90 pounds.
I don't know what I call it,
Without the-
Delta crane sort of thing, where he's got
Yeah,
three servos,
go up
and
a
it's
hill.
like a trapeze.
You gotta push
Kind
up,
of grab,
you
but
gotta pull at least half of it.
it was pretty large.
So,
I mean, larger than
be able
this,
to
and I just
just
decided
stand up
that
on it. Have to have probably
you start taking
45
off
pounds.
everybody that were recording.
This is too
You might
much.
want to tell
I
people.
think he just recently designed one that uses the standard servo.
All right, FYI, we are recording the session, so you're all on camera.
And those plans I was talking about do not exist.
So, fair
Is there
warning.
audio on this?
Yeah.
Okay. So there's audio being recorded as well.
Yeah, it's hopefully gonna be like you wanted. You
Right.
can watch the screen, or you can watch the.
Right. No, I'm all for it.
Of course, the screen's far away. Maybe I should move the.
Yeah.
Camera
but,
closer.
It's called a scrambled dragon egg.
Yeah, why don't you put it over there and I'll move that chair for you.
I should have set up the.
Dude, I don't like to drive here anymore.
Okay. Let's do this.
This is 34 pounds.
I'm gonna go. I can't disconnect. Well, actually, I can disconnect one.
No, I was surprised when I got there, I didn't know if I get the
Yeah, it's a little steep.
Thank you.
I went back over here, watch out for Robert. He's a little mischievous.
Yeah.
What's the best way, like this?
Face, I guess, yeah, face dead on the screen there.
You can sail. Any good advice?
They're not a
Yeah.
bad price anytime.
Yes.
They're probably got
Yeah, they sell a lot of stuff that's kind of unique to them. I mean, you can kind of beat them on some of their gear motors, but like their little motor drive boards and stuff, they're top quality, and
Oh, you brought some too?
Yeah, I did.
that's their A-star right there.
Did you bring those in there?
Yes.
You already cleaned it up?
Yeah,
Once
I'm
we go
not
to
gonna
1
worry
o'clock,
about it.
should I bring something
But I'm gonna
different?
put them out here.
No, I think that's perfect.
Donuts are still good?
Yeah.
I have it.
Yeah.
Yeah.
Right.
Very
I
good,
had a
thank you,
couple
Josh.
No, I mean, if we're talking about going to 1 o'clock, as soon as we get approval.
Oh.
If I'd have known, I would have stopped by QT.
Fully.
Oh, that's doing my. 204, yeah, it's now 3 times.
The internet frequency, but it is not being mistaken with connecting to that.
I'm supposed to put up a sign, but I haven't yet. Sponsored by Tesseract Mobile.
You can program it where.
Sponsored by what?
Tesseract Mobile.
The way I
So
program mine.
your company is actually,
You can imagine.
the one that buys the,
Yeah.
really, thank you.
And now I have
So,
Yeah, he's spitting the bill on that.
yeah, no, I'm not just like, we're not spending the club's money willy-nilly on whatever I decide, like,
Not yet, at least.
no.
plug that into my laptop.
We're still
Remote
shopping.
controller
I
Yeah,
have a little program that makes it like your.
allows you to remote control over your
Correct.
local Wi-Fi network, a robot rover,
Here,
on your Arduino Uno, and Wi-Fi shield, and
Reset,
start from
transmit your
mother's platform.
program.
That is
adjustment,
interesting.
it resets everything.
Something to look at.
And then,
Yeah.
like your
Show this to,
service,
you know,
straight across, no problem. You're limited to.
what is that?
about 50 feet.
robot controller.
Say I've never tried
It's the
that.
application that allows you to remote control over a local Wi-Fi network. The robot rover through your Arduino Uno and Wi-Fi shield, and start from mother's platform. That's a good question. Got a guy here from the name of Dario, the tooling or whatever his name is. I don't know if that's the pronunciation right on that.
That's a lot like what I'm working on.
Yeah,
Yeah.
you should go into business on this stuff. Guys. I know you have other things to do.
I'm gonna release it. I should. I got a hang up about, like, I don't feel it's right
Yeah.
to release. Like, it's too early, but
Yeah.
I should just put it out
I mean,
there.
they've got
and
here
just
one from
let
Lego
everybody
Mines,
know.
they've got a robot commander here, Lego Mindstorms. What about Lego Mindstorms? They've got one here, robot commander, Lego
Small,
Mindstorms.
like a toy?
What is that? That's a good question.
Okay.
Bring that out. Mindstorms is what all the kids. Yeah, I know.
When mine goes out, it will be free. It does everything out for
Yeah.
already, so
Yeah.
it'll be free. I'm not sure. I'll probably do some kind of add-ons.
Yeah. Connects via Bluetooth to the EV3 intelligent brick. This easy-to-use app allows you to interact with your very own EV3 robots without even connecting to the computer. This means you can play instantly with your own robots.
Alright.
It's moving a step in the right direction.
That build.
Oh, Adam, should we get started?
Get dirty now.
Yeah.
And it's
You want
up
me to close
past
the door real
10:30.
quick?
A
Yeah.
lot of slides. Yes. Okay.
Okay.
Done a lot of
Okay.
So we start with the intros. I'll start since I'm just, one. All right, I'm Josh. I do software development, Android.
I'm Robert Levitt. I've been a librarian for several years. I have done computer programming. I'm learning Java right now. Hopefully in a few months I'll be a Java programmer. I can go from there. I'm interested in robotics to a certain degree. And I'm hoping eventually to use Java to work with robotics. I'm Dan. I build robot sensors.
Craig, I'm my pay-for life. I'm a software engineer and developer, and got an engineering degree and a computer science degree. So I really do robotics is my hobby, but I did my master's is in robotics and intelligent systems, which is doing the presentation today. Years ago, I did work for several years. I did robotics, machine automation, plant automation work. It's always been a passion.
I'm Mark. I do instrumentation at a refinery. I've been an electrician and programming is my hobby. So dabble in a little bit of it.
I'm Donald. I have a great interest in robotics and also trying to get on board with full stack development, JavaScript.
Jason, do product development and machine and industrial design.
I'm John. I'm a retired organic chemist, and I'm here to learn.
I'm Dave. I'm interested in home automation and electronics.
I'm Steve, I'm retired also. I like home automation some, but also renewable energy.
My name's Adam. So in robotics, I get involved in a lot of different projects, made numerous robots. So if there's any questions on anything in particular, you can ask me. I'm always willing to help.
I'm Zach, machinist by trade, so I'm more into making robotic parts.
I go no. Back, Doug.
I'm Brian, programmer by nature and training. And currently I'm doing data analysis. Raised 2 robotics people.
I'm Andrew, recent graduate of Missouri S&T, on computer science. Not really doing anything robotic type stuff right now.
Actually, who's next to you?
Who's next?
Hi, I'm Dave. I just finished summer school, so that's the extent of my official robotics for a while. And I've been interested in robotics since I realized model trains can be automated. Anything can be converted to some part of a model train. That's my concept for my next topic.
Okay, Craig, it's all yours.
So got a lot to go through on this. This is so sorry if I'm going to go through it a little fast. We want to keep it the pace and not bore away too much at the same time. My expectation here is when you get done with this presentation, that you're not going to be able to go out and program a SLAM system. It would take half a semester of a graduate level course to kind of get into all the nitty-gritty details. Good news is you probably don't. There is a project called OpenSLAM that is out there that has most of these algorithms available. ROS, which we've talked about a lot in here, is kind of our go-to robot operating system platform, has modules that want you to do this. So what I want to do with this presentation is really have you understand what's going on behind the scenes, so you know how to do some modeling and there's a lot of math to it, a lot of statistics and stuff. And it just would take a long time to go through each individual piece. So hopefully I'll get the right level for everybody, a little bit of detail where you go on the math. So SLAM is an acronym. It used to be called something else, MALS, or they rearranged the letters. They thought finally SLAM was a cooler acronym. So they started calling it something different. But it stands for simultaneous localization and mapping. And it's an algorithm process that you go through when you don't know where you are in the world or what the world looks like. So you don't have a map and you don't know where you are specifically in the world. So you can think of a scenario of a robot, let's say a snake robot, that is being used at a building collapse. And you want to put the snake robot in and have it crawl around and find people in the building. It needs to ways to go and explore. So it crawls in little ways, recognizes objects, crawls through and does a exhaustive search of the maze of the rubble. It has to find its way back out too, so it needs the map in order to figure out its route plan and how to get back out. That's an example. Walking into a room, a robot drone flies into a room full of terrorists, and it starts to look around, see where people are, see where the walls are, and then proactively explore the area. So those are just a couple of ideas of where you would use this. It can be used in other areas. It can be used where you start with a map and just, and the reason it's helpful in that area is it's very, one of the options we're going to talk about is very resilient to people and moving objects in a room. So we talked about a robot that we want to build here for the Science Center. What do we do about people just suddenly moving front? Okay, this handles that to a large extent. So I'm going to want to talk a little bit about that too. That's the goal. Big thing to know is it's an approach. It's not an algorithm. And that's why I said there's a lot of different opportunities you have out there. There's different hardware you can choose for the sensors, different algorithms, different approaches that you can apply depending upon what it is, what your environment looks like. 3 steps in SLAM. We'll talk about those. I'll describe them in a couple of slides. Then we're going to go through a bunch of detail on those steps. Then at the end, we're going to wrap back up and show how all the different pieces then wrap back up into those 2 steps. So I use for that here, we use a thing called focused on extended Kalman filter. And the Kalman filter is a technique of taking multiple inputs and deciding which one is the most trustworthy and finding out how you judge your position and the position of landmarks in the environment based on sensor readings that are conflicting. Yeah.
Should we ask you at the end of your talk, or you have to the question?
Whenever you got a question, I think it's easier to do that. Yeah. So when I say a complete solution, I don't mean a perfect solution. There's issues. This is an example solution, something to get you started. There's a lot of ways to improve these and tune them. And if you look at the research, papers on the internet, a lot of the stuff you're going to read is how do you take this algorithm and tune specific things of it to be better. So I think this will be helpful to see the overall broad picture. And if you're interested, you go in and find the details of the implementation. Also, another thing we realize is this isn't even in the industry, is not a completely solved problem. There are situations that people just don't know how to fix yet. So that's one of the cool things about robotics is that it's it is something we can all kind of get into ground level on some of these things. All right, what is the SLAM process? 3 steps to the SLAM process, and they happen in order iteratively. Your robot is taking time steps, right? So every 10th of a second, every 1 second, every 100 milliseconds, or every 10 milliseconds. However, whatever your time slice is, one of the things your robot's doing is these 3 steps. So it's just take it, and it builds up that over time. So it starts at time 0, does 3 steps with all the 3 steps, and it goes to time t plus 1, does all the steps, t plus 2, and it's edited. And the thing that the extended Kalman filter does for you is, despite all this noise in the environment, it starts to very quickly in 5 or 7 time steps, start to zero in on very accurate solutions that are maybe 3 to 5% off where you really real, despite all the noise. So the first step is they update the current estimate using odometry data. So the assumption is that you've got something measuring your odometry, how far are your wheels turned, how much you accelerated or decelerated, if you change positions. So you use mathematical physics, the physics that you used in high school to say, the equations of motion, velocity or position equals velocity times time, or acceleration times time, kind of equations to predict where you were, and your odometry says, I should be at this time. Okay, that's the first step. The second step is you keep estimates of your sensors observing landmarks. We're going to talk a lot about what landmarks are and how they operate, how they apply here. But you can obviously, your sensors are going to be able to pick out landmarks in the environment, and you want to reobserve those. So you use those estimates to say, well, I was here, and I found these landmarks in the environment. When I move a certain distance, those landmarks should now be relative to the robot in a different position. How close are they to where I think they should be? That's going to give you your second estimate on your position. So the first step is your odometry predicts you should be here mathematically. The second one is through triangulation of these objects you're watching back to where you think you should be, gives you another estimate of your position. Conceptually then, the Kalman filter takes those 2 inputs and tells you which of them to trust, or how much to trust each one. The third step then is you add new landmarks. As you move forward, people move out of the way, the new landmarks show up. And so you put those into your system to be used next time. That's the third step.
You're not using things like distance measurements, like Connect, infrared, or
you could.
sonic?
You could. I said I'll talk about that in the slide, but the sensors you could use are varied. And really, we'll talk about one of the last slides is about how you choose the right sensor for the right environment, because different sensors are going to give you different information. And you want to tune your sensors to what's available in the world, so you're getting back to the right stuff.
Hardware allows you more resolution, depending. So, like for example, you could use the SLAM situation if you had like ping sensors, but the resolution on a ping sensor is not very high.
Yeah. So you use SLAM algorithm not just for robots. They use it a lot for missile tracking. So if you've got a missile that's tracking an object, a plane or an incoming object, you want to shoot it down, your radar is not precise. You know, it might be plus or minus 5 meters, but you want to be sure the missile hits the plane or hits the object, whatever you're trying to shoot down. So you're taking your radar signals and you're using the SLAM algorithm to get a better prediction of where the plane really is, given this radar signal that might be, 15, 20 feet varied. So you can hit, and then your missile hits the SLAM point, it doesn't try to track this moving piece. So it can be used in a lot of different areas, and then different sensors will give you different applications, but the process is all the same.
In the case of people being in a room and the first time it's been there, does it tend to, if they're standing still, tend to say that's a landmark?
I'll show you why.
Okay.
Yep. So the other, couple other just basic things here before we get into the algorithm. We'll talk about the robot itself. Most all robots can be modeled as a single point. And so the typical way of doing robotic tracking and localization is to say my robot is a single point with no dimensions and treat it as a unicycle. So it can rotate and move forward and backward, but it does so as a point, not as 2 wheels, not as 4 wheels. And you can do a 4-wheeled robot with steering, and you can still model it as a single point. There's a whole other lecture we could do about architecture, how this fits into a big stack architecture, where you convert from the point unicycle model to a steered robot, what your actual configuration is. That might be one for a different day. But what you do is, so let's say your robot is 2 feet around. You treat that as a point, but you don't want to have to hit stuff. So if my robot's really this wide, I consider it to be a point, my algorithms could take me in impact objects. So the other thing you do is you develop what's called a state space. If you have a map, or as you build out your map, you make all your features bigger in proportion to how much you made the robot small. So if your robot was 2 feet across, you add a foot to the size of all the objects you detect. And that means you can use your robot as a point device. You just expand the buffer zone around all the objects. Okay, that's sideline to the SLAM algorithm, but it's something we want to be sure that we're thinking about as we do this, or why we can treat this as a point. The other thing is then the sensors. And for the example we're going to use here, I'm going to use 2 different types of sensors, a laser sensor, and assume the error of the laser sensor is plus or minus 50 millimeters. That's probably really generous for a laser now. Probably 5 millimeters is probably more like it, but there's still a variance. And then for your odometry sensors, I'm going to do wheel encoders on the robot. And the errors in the wheel encoders are less than 2 centimeters per meter move and less than 2 degrees of error per 45 degrees of rotation. That kind of sets the bounds of only using the 2 measuring devices, what they are. Okay. So here's the basic SLAM workflow. So the odometry of the robot is erroneous, but it uses an estimate. Every measurement is an estimate. Nothing's ever measured precisely, and that's the real world. So the laser scans we can use to correct the robot position. We talked a little bit about that. So, and then extract the features on the reobserved elements as the robot moves. Moves is a relative term. Really what it means there is as time clocks on, right? So the robot doesn't have to move to do this, but time progresses, and you do this every time step. And then you apply the extended Kalman filter to update where the robot thinks it is, and this Kalman filter keeps track. It's the math inside the filter tells where the most likely location of the robot is. And so you kind of look here in the flow. The laser scans are coming in, doing the landmark extraction. Data association is taking the landmark you've identified and seeing if they're in a list of the landmarks you've seen before. That's what data association is. And then the odometry is coming in to update the Kalman filter with the odometry data, predicting where you're going to be mathematically from the old spot. And then you're going to do the reobservations, which is looking for the landmarks you've seen before. Have you seen them? You still see those? Have they gone away? Did new ones appear? then the new observations, that is, sorry, the new ones appear. All right. So at any point, we talked about it before, at any point, the EKF does not have the current position or where the robot thinks it really is and what the world looks like. So odometry changes happen when the robot moves, or just if the robot's completely stationary. Because there's a variability in the sensor reading, stationary robot, stationary room, you're not going to necessarily get back the same reading time after time after time for the sensors, because there's no noise in the measurement. Let's see here. Laser scanners. I said we're using laser scanners to extract the environmental landmarks. We associate the landmarks. I think I've said most of this already in the previous slide. Yep, we've already talked about this. All right. One more sort of bookkeeping preliminary step is a coordinate system. There are two coordinate systems you maintain. The local coordinate system is the coordinate system of the robot relative to itself. So the X coordinate will call out the front of the robot the normal direction of travel of the robot is the X direction. The Y direction is perpendicular to that out the side of the robot through this center point that we're modeling the robot as. We also have the world coordinate system. The world coordinate system, I call it, is the WCS. The WCS starts at some fixed point in your world. Doesn't really matter where it is, but it doesn't move. Might be the starting point of the robot, the charge station, an unmovable, absolutely known point landmark that you're going to say this is 0, 0 in the world.
Can you start with just whatever you have and you put it turn on?
You can. You can start with that.
I don't know what this is yet, but I'm called it 0.
Yeah, wherever you power up, that could be 0, 0. It could be, the whole thing just has to stay the same spot forever while you're running. All of your sensors and all of your odometry data, especially the sensor data, all come back in terms of the local coordinate system. So as the laser scan spins around, if the robot's pointed this way and spins, it pulls certain pieces of information. If it rotates 45 degrees, it thinks these sensors or these landmarks have all moved, but in reality they haven't. And so you need to convert all of your readings eventually back into the world coordinate system coordinates. And there's simple sine, cosine, rotational matrices. You need to look up a fine matrix or two-dimensional rotational matrices. I'll show you how to do that, right? But it takes the coordinate systems from the local coordinate system that should represent those numbers in the world, or take a world coordinate system number and tell you what it is relative to the robot. So you'll need to be able to do that.
So you'd kind of be tracking yourself on an XY grid, would you say?
So you typically do all the work in the world coordinate system. It could be a grid. You could block it up in cells because that's very convenient for route like higher level things. For this specifically, you don't need to have a grid. It's points, right? So it's a number line. So you could be 74.234, perfectly legitimate number for an X coordinate or for a Y coordinate. Yeah. But all of your numbers really need to get pulled back into the world coordinate system so they're consistent. So you need to know what the angle of the robot is relative to the world coordinate system, and then the angle of the center of mass of the robot.
That's kind of why I'm asking, is because if you were turning 15 degrees and going forward versus turning 30 degrees, your X and Y, the change as you travel is going to be different.
Right. Yeah, and that's why both of them are legitimate. Numbers are exactly the same point, but they're relative to two different spots. So in order to have it consistent, where you can compare object to object, you put all of these coordinates back into the world coordinate. So the robot finds something, it says, okay, I shoot my laser over and I see this wall. I take that wall, I don't look at it relative to where I am right now. That's going to change. I convert that wall back to the coordinate system, which maybe will go every time. So it's always consistent.
Do all these techniques apply to 3D space as well?
They do. They all apply with this, you know, equally to 3D space, you just have the third dimension to deal with. You change your sensors. So for 3D space, for instance, and even for 2.5D. So robots walking on a flat table on a flat room, it's all cool, right? But if you come to a ramp, if you have a horizontal laser sensor, you're going to strike that ramp and you're going to think it's a wall, right? So it's going to be misleading. So for 3D spaces, you really need a vertical and a horizontal laser sensor. So the horizontal is seeing certain space, but it can distinguish ramps from real obstacles by having the vertically oriented line scanner too. Everything all applies the same way. Yeah. And you can do it, when we get into the matrix math of all this, it just means instead of a 2x2 matrix, you got a 3x3 matrix. So the 3x3, it's actually a 3x3 matrix we'll deal with X, Y, and theta, X, Y, and rotation. In the case of multi-dimensions, you'll have X, Y, Z, and then theta, phi, and phi, because you'll have all three of your angles that you have to do. Because you could be this way, roll, pitch, and yaw, right? If you've got a 3D system.
Extra dimension adds to each individual axis.
Yeah.
And it can be done with like a laser scan. Usually we add like a rotation motor on the laser scanner. So instead of just getting a Cartesian level, you're actually moving the laser, so you're getting more data. So then that's another thing. And that's another reason why when you're using a origin system is because the mathematics are more simplistic. It's easier to crunch the numbers that way than having to take into calculation the complete, origin of the robot, like all individual axis points of it, which is mathematically it's much more.
There's a cool video on YouTube. They built a robot. He doesn't use a laser scanner. He uses a laser rangefinder as a point, and he put the laser rangefinder on the end of the data factor, a 3D, and the thing goes around just going like this, looking all around trying to find stuff, and to solve that problem. It means you have to have a planning algorithm to figure out where you want to point the laser. But
For every bit you capture, now you got to do some sort of math with it. So why not just do two things, X and Y?
Yeah, it's a trade-off, right? Yeah. And how fast you have to move and all these things. Yeah.
Also becomes relative to really care.
Yeah.
Are you gonna go up there and interfere with the ceiling at any time?
But you could be using things in the ceiling as
Right, in mind,
as
and then
landmarks.
it would be right.
Yeah, so you could, because they're not going to move that much.
Yeah, the North Star system actually developed that application. Instead of mapping what was on the ground, they usually just use sensors to detect obstacles, and then use the airspace, so like the walls, and then because they will fix. No one's going to be messing with it.
All right, so let's go into a little more detail now about what the robot does in its flying system. So the robot takes an initial measurement of the distance to its landmarks, and we're going to talk about how it does that later, but kind of go through it at a high level the first time through. So it finds that distance in the world coordinate system. Then the robot moves ahead a little bit. So it uses its odometry. Its wheel sensors tell it the wheels have turned 14 degrees. At 14 degrees based on the geometry of the wheels, what that translates to in linear motion and in rotation, because one wheel might rotate more than the other. So based on that, the equations of motion, the robot thinks it's now where the dark blue robot is. The stars haven't moved. So that's all it's done is moved itself forward. Okay, the next thing then is it does a scan and it finds where those landmarks are. The landmarks haven't moved, presumably. But the sensors, the landmark position, when it triangulates back from the landmarks, that's telling us in a different position than the odometry is telling, because of noise in both systems. You don't know which ones or how much both have noise has contributed to both of them. So which one do you believe?
So the sensors that you're referring to in the first bullet is actually your laser sensor.
This one?
Yeah,
So
you're
this
saying the laser sensor doesn't match the odometry sensor.
Right. So you go out and you find existing landmarks, and you triangulate back from them, and it tells you you're at X1, Y1. But the odometry, the math of the odometry tells you you're at delta X, delta Y. So which one do you believe? Because you're really a blind man reaching out, touching the elephant, and you don't know exactly which part you're touching, and you have to And so the crux of this problem is, how do you figure out where you really are based on these conflicting pieces? And you can actually end up being more accurate because of it. All right, in reality, the robot's somewhere, we'll say somewhere in the middle. Doesn't have to be, could be way off, but for our purposes, we'll say reality is it's somewhere in the middle.
Yeah, best case scenario.
Yeah. So the term that I don't like, but it's you, this I didn't pick it, so don't blame me for it. I think it's a horrible term. It's called the innovation. The innovation is the difference between where the sensor says the robot is and where the robot really is. Okay? And just remember, innovation is the error, right, between where you really are and where the sensors think you are. Because we're going to use that term later on, so just keep in mind that it's a term that makes no sense to me in that context, but that's what's used. All right. The extended Kalman filter quickly zeroes in on a good guess, right? So it takes all this information and it uses a Bayesian technique. So Bayesian is a statistical approach to statistical math. And it uses the statistics knowing how much error distribution there is in these sensors. And it figures, okay, given these distributions of error, what's the distribution of positions I could be in? I have a 2% chance of being here and a 2% chance of being here and a 98% chance of being here. I'm going to say I'm here, even though that's not what the sensors are telling me.
And how do you figure out what the shape of this distribution is? How do you figure out?
We'll talk about that in a second. That's the complicated math part.
Okay.
But we will talk a little bit about that. All right, world's a noisy place. We all know that. We do robots. We've got robots run off the edge of the world and go crazy and chase us and whatever. There's inherent sensor inaccuracies, echoes, reflections, precision issues with field encoders especially. The encoders have the slots of the encoders are a finite difference apart. You know when you get a transition, but you don't know where you are in the slot or in the solid in between there. That can be half a degree sometimes, maybe a degree and a half of variability. Slip, one wheel hits different terrain than the other one and it turns a little bit. The encoders, the wheels move what the encoders say, but the robot didn't track well with the encoder. Temperature, humidity, you got a sonic sensor you brought over here. If you're using a sonic sensor, it assumes standard temperature. So the speed of sound, that measures how, it's an echo. So it sends out a sound first, and it measures how long for it to come back. The speed of sound is different based on temperature and a little bit humidity. So if you're not correcting for temperature, humidity, or there's errors, variability in your temperature reading, you're going to get noise in that sonic sensor. And just the repeatability. The real world is same sensor hitting the same object 2 times in a row aren't going to necessarily give you back the same answer every time. There's also system inaccuracies, and these are very hard to come up with and think about. But propagation delay. You're working at nanosecond scale time frames. The propagation delay of a network is important. The faster your robot moves, the more these things are important. We're talking about the drone I want to do, the autonomous quad motor I want to work on. And it's much different when you're walking at 2 miles an hour through a room and responding to a changing environment versus a drone that's flying at 80 miles an hour. You're flying at 88 feet per second. 1/10 of a second of propagation delay, is 8-9 feet of travel. Well, that's just to get the signal. Now you got to recalculate a flight path and then have the drone react to change the plane to do that. Well, if you're flying at 80-90 feet per second, you've traveled 20 or 30 feet before you even start to affect the drone rotation. Probably already hit whatever you're going to hit unless you've got some really good sensors. Propagation delay matters the faster you go. Synchronization is another problem. All these sensors are not measuring at the exact same instant in time. And so you need to be able to do their interpolation or extrapolation at a timestamp to align them as best you can. Otherwise, you're introducing more noise into the system. Any others that anybody's experienced or run into?
Not so much experience, but you mentioned the precision and slip, and I'm thinking the design of the Omni wheel would probably be the worst when it comes to slip.
Yeah.
But you despite being so agile and
They don't, yeah.
Well, the difficult with the Omni wheel is how do you encode that? Because it has multiple points,
they can be going sideways at any time.
So you would have to do, once again, you do some mathematics on which wheel is spinning in which direction, and then calculate between triangulation of however many 4, 3, motors we have. But slipping is a big problem. That's why we typically don't rely on encoding. Usually the laser is going to be more accurate than the encoding, the odometry. But yeah, it's a problem, and lasers aren't always accurate too. We're talking about occlusions and all kinds of things. So it's never a perfect system, like you said, but it's good enough in a controlled environment that you can actually get some decent results.
And surveyors have had to deal with this problem since they started surveying. And one of the things they did was they came up with a standard length chain. And they would have these markers that would be separated by this standard length chain. And they used that to measure off things. Of course, their accuracy was still a little, crappy. But yeah, I wonder if that would be something that would work in this
That's basically
environment.
what's happening.
If you could put
in the
your
world
own artificial landmarks in there that are separated by a carefully measured distance.
Could, as a different algorithm, right? Because the idea behind the SLAM algorithm is you don't know anything about the world.
Yeah, you don't
You have to discover it as you move in.
I see.
And that's where the discovery process is part of the inherent noise in the system. So we know from our experience, at least our intuition, that in a noisy environment, it's very hard to make these rigid predictions of the massless elephant on a frictionless plane, things we do in class, in school. It's very hard to walk into a room of moving things and lights and things and be absolutely precise about what we're doing. And so algorithms that the robot would try to use that rely on absolute precision are destined to fail because the world they live in is imprecise by nature. So it's oil and water.
It's hard to, you can't even position an atom in fixed space. So how are you aiming it's impossible?
Yeah, and so
as humans, we do this calculation on our own very quickly. We have our own common filter in a sense after these statistical values that we get from our experience in the world. But robots, just because by their very nature they're mathematics, they are looking for precision, and any deviation from that will affect it, depending on your algorithm.
makes them very fragile. Yeah.
I was just going to say, picking up on what Adam was talking about, sometimes you do have these, typically in these situations, you have sensors that are very accurate, like, for example, a laser scanner. And then these other sensors, such as an odometer, that's not very accurate. But the problem is a lot of times that accurate sensor just can't update at a fast enough rate. And so what I've seen, for example, on missiles, is what happens is they'll use GPS to come up with their location. The problem is they can't update fast enough for them to use that solely. So they, in between GPS updates, they do this navigational,
Extrapolation.
Extrapolation. I don't know what kind of sensors they use for that, but so they're updating at a fast rate.
Yeah, they're checking how fast it moves.
And then they're using the Kalman filter to.
Right. It's all basically very similar, like you were saying, that they use this formula in a lot of applications.
Right. And so the Kalman filter allows you to use this.
Use all this data and you have some data prep, right? So you're taking some of that information in between sort of resets. Like you say you're going to trust your GPS. Well, that's one input to the Kalman filter, and then your odometry reading, which could be wheel sensors, it could be accelerometers, right? Because those could be very precise and faster reacting. So you might be doing every 100 milliseconds, you're doing the GPS refresh, but in between there, you're doing extrapolation or you're estimating your position based on line view or accelerometer or something. And you don't know if it's accurate, right? So the real world is how do you take all these inaccurate, fuzzy numbers and use them all mathematically to come up with what ends up being a surprisingly very precise estimate of where you really are and what's really happening. And that's where it's at the math. Simple math gives you simple results sometimes, but it doesn't necessarily fit the real world. It's a good first order approximation using equations of motion. But when you're really flying a real robot or driving a real robot or shooting a real missile, you need to be more precise than that.
So the
Because
faster you refresh your sensors and your mathematics, the more accurate precision you're going to have, because, it's saying.
But even to your point, if you've ever taken, you can use Android, they don't have a really good screen for it. You can do it in a test mode in your Android device, set it down and it'll do the GPS test. And the GPS in the Android running as fast as it will go will vary by 30 or 40 meters, just all over the place, because a plane flies by and you get a reflection. If you're buying super expensive, a $2,000 GPS sensor, you're going to get stable, accurate results. If you're buying the $4 one they put in a phone, or the one you get from wherever for $6, it's not going to be as stable and accurate. It doesn't mean it's not usable. It just means you have to do other things to compensate.
So if you have a robot in GPS, like a lot of the times we'll build Arduino robots using GPS, they're accurate to a certain range, and that's dictated on the amount of satellite information you can get.
Right.
Satellites,
Right.
the trajectory on that is necessary. So
Yeah.
the more satellites you have, the more accurate position you can have.
Right.
Also, refresh rate is the most important. I think how fast can you cycle that, and then take those estimates.
In personal experience, like at the refinery, I check flow meters and I work with valves and things, and they're expensive stuff, and our flow meters are very good, but no matter how much money, they're not perfect, and the valves can't react instantly, besides the fact that the flow meter has to talk to the computer has to say, oh, we need less valve, so go talk to the valve, so you get that propagation delay.
Right.
But in our case, almost everything could be good enough, and then we're just trying to steer in that band of what's acceptable.
And that's a whole different discussion here too. Like, you get into the dynamics of this thing. If you're correcting your robot, you can get into oscillations, you can get into weird things to have it do because it's reacting to things that are out of sync. And dynamic stability is a whole different topic to have. But using these time cycles and having the loop you're going through and getting your data fast enough and the reaction time of the robot fast enough that you don't get it oscillating like this, trying to track to a stable point that it's trying to get to. That's a whole different thing. Let's go ahead and talk about landmarks and landmark extraction, which is the first thing that the SLAM algorithm tries to do. Landmarks need to be things that are easily distinguished from the environment. A very broad, open statement. We all can understand that, but getting a computer to realize that can be tricky. Depends on the environment, right? Environment by its definition is an abstraction. If you're inside, walls, corners, doors, what about furniture? What about lights? Can be, right? People use lights, the strobe lights some people put up for robots to track by as a form of a landmark in films. Lights can be turned off. Lights can be repositioned.
Get weaker with time. Intensities get weaker with time.
Intensities can change, right? You turn a fluorescent light on, it's very relatively dim for the first minute or so, then it gets bright after a couple of minutes. It's not consistent. They strobe. So if you're in a room with fluorescent lights and you've got a camera taking your pictures, you get this weird oscillation between the 60 hertz of the lights and the 30 hertz of your 35 hertz of your camera, where you get things fade in and out, weird. Sort of positional, different glare and reflection off the lights can be a problem for cameras. If you're outside, what do you get? Well, you still got walls, you still got different kinds of walls or different relative position, but there's probably buildings around, especially trying to navigate corners, doors, trees, sidewalks. There's a lot of things you can do outside, but they're different. And we touched on this earlier, and this is where I really want to hit on it, is the sensors that you choose really have to be tuned to the types of landmarks that you want to try and detect. So if you're going to be outside, things tend to be farther apart. So you need longer range sensors. Different environmental conditions outside. Wind can move things. Trees have a much different reflectivity than than a wall inside or a chair or something. So you have to choose your sensors to match the kind of landmarks you're going to be looking for. Key traits in a landmark, they have to be easily reobservable. So you rely on seeing the same landmarks over and over again, time step after time step, and recognizing where they are so you can triangulate your position back. So if there are things you can't see or you can't see very often, they're not a good landmark. You distinguish it from one another. So two landmarks that both look the same within your field of view, you can mistake for each other. I have two pillars in a building, and I can only see 10 feet. Pillars are 30 feet apart. If I come up to one, that's the only landmark I've got. I really don't know which pillar it is. I'm going to misguess, right? So you've got to be able to be sure your sensors can reach out far enough to get enough landmarks you can really understand where you are in context. So the plentiful in the environment, right? Too plentiful can be an issue too, because you can't see the forest or the trees. Not enough is a problem because you can't. If you're out in the middle of a field and you have no landmarks, you don't know where you are yet. If you have landmarks that look alike that are far apart, you have a problem. They need to be stationary. If they're moving in a way you can't predict, you can't try to that back to you to figure out where to go. So we're going to look at two algorithms really quickly here on landmark detection. They differ based on the types of landmarks you're going to look. They're usable with laser sensors. The first one's called the spike algorithm. Spike uses extrema, radical rapid changes in distances to find the landmarks. So they're going to rely on landmarks that vary a lot, like a tree in an open field or pillars with an open background. They're not good if people in the area because Spike tends to find people as a landmark. And for a lot of reasons, they make poor landmarks. They move. You don't really you can't rely on them to be in the same place. The other we're going to use is one of my favorite general purpose algorithms called RANSAC. RANSAC is Random Sampling Consensus. Has anybody ever used the panoramic view on an iPhone? You do that? That uses a RANSAC algorithm. And what it does in the phone is everything that takes a picture, it runs an algorithm that finds features in that picture, like edges, corners, things that change in the pixel. And then it goes to the next image and it does the same thing. And then it draws lines randomly between the two images, between those interesting points. And it keeps doing that in random ways until it finds a situation where all the lines tend to be parallel horizontal. And that means that it can now line those two things up, and that's how it stitches the image together. So while that algorithm is going to seem very computationally expensive, and it can be, it's surprisingly easy with modern computers to do it. But the RANSAC algorithm is good at extracting lines from laser scanners at point clouds. Is really where it does good. And you see a lot of, its goal is to find straight lines, where Spike tries to find things that are different from their environment, from their background. RANSAC tries to find straight lines in their environment. Walls are good straight lines. It's also why RANSAC's good at identifying and ignoring people. People in a laser scan in a point cloud do not come up as straight lines, they come up as curved lines. So RANSAC can actually ignore curved lines, people, and find walls and straight edges really, really well.
Why do they come up as curved lines? Because they're moving?
Because they're curved.
Oh, okay, gotcha.
So here's an example of Spike. I'm going to talk a lot about it because I think it's limited applicability in a lot of situations, but it's still an interesting and a pretty cheap algorithm. So you take your laser, scan the room, that's what the picture here is, or the return of the point clouds that come back from the laser scan. And what you want to find is two consecutive data points that differ more than some threshold. And your tuning parameter here is the threshold. So you may say a meter, or you may say 10 meters, or half a meter, whatever you want to do. And then you identify the returns that come back that, for two of them together, show an edge. There's a better way of doing this, which is you take 3 consecutive laser returns. Because laser returns come back as the whole rotation comes back as, let's say, 360 range returns. So you take 3 of them, called A, B, and C. You subtract B from A, you subtract B from C, and you add those two numbers together. When you do that, if that resulting number is over your threshold, it represents a big transition. And you can work the math out yourself on that. But trust me. So what Spike is doing is going around is finding flat, 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 flat. Oh, there's something there. I'm going to take this as the first edge, and then it finds them here, and then it finds one fall away. It's like, okay, that's the other edge. This is my object. Now this is my other edge. So that's essentially how Spike works. So environment, it works better outside because it finds things like trees and things that have a lot of depth of field. It distinguishes those really well. Obviously, it's going to find people just as well because it's going to go along, find a person. Okay, that's a person. It doesn't know it's a person or a tree or whatever. It looks a lot the same. Just find out. So in this picture, the orange dots, I said red, really orange as it came out, but the orange dots represent extracted landmarks from this table legs in this case, from a laser scan using the Spike algorithm. So other lines were walls or parts of the table or something, and it pulls out the legs from the poles out. That's how Spike works. To me, the more useful one for us is called ransack. It's the random sampling and consensus. So you take your point cloud and you take two random points picked out of that point cloud, whatever you want to do, and then you draw a line between the 2 points. Extend the line out to really array because you can extend it out infinity on both sides. And then you do a least squared approximation between all the other points in the point cloud and that line. And that's going to give you a best fit. So you record that number. Then you pick 2 more random points. You do the same thing again. Do the least squared approximation to the points. This gives you a correlation, a variance of how closely all the other points fit to the line you want. Straight lines will be the point where that least squared approximation will be the best fit curve. So you just start randomly taking points until you find the one that gets you the closest to the dense line of points that you're in. Okay. Mathematics, it's an AI technique actually, because it's not deterministic. It doesn't guarantee, unless you try every combination of points, it doesn't guarantee that you will find the perfect best fit line. But the one thing it does do is the longer you let it run, the better it finds stuff. So if you're in a time critical loop, you can quit early and probably be good enough because you may not find that line on the right that fits pretty close, but you might find one that's pretty darn good. Okay, and so you can control. You have control over the variability and how long it goes. So you can find good lines quickly, or you can do an exhaustive search and you can spend more time. But eventually, the idea is that you find the one that's as close as you can get to the best one. This is an algorithm you can apply to many different things. Computationally, it does a lot of math, but it's very quick. And in modern computers, it is not something you can do at a few dozen milliseconds. Okay. Quick pseudocode for that. I won't go over it exactly line by line. I kind of talked about it before, but this will be, you can use this, you can back to a video or a presentation and pull this out. This is also online. But the idea is you just grab these different points and you find the ones that are mathematically the best fit, and quickly you found the best one. Here's an example of how it does it with a person. So on the left is a laser scan of a cluttered room. 3 walls, and then a couple other small walls, like the upper, that's sort of vertical in the picture, but it's a diagonal wall in the room. And then various noise pieces that came back. By running the ransack algorithm, the lines on the right, the green lines, show you what ransack picked out as the walls. This is where we said ransack tends to be able to find flat surfaces really well. And so that's what you're looking for inside a line. They found a person. There's a person standing there, circled in blue on the right. You see, that's a very distinctive shape, not a straight line. And so ransack will identify that, won't identify it as a person, but won't identify it as an object of interest. You can see it also ignored a lot of points that were outside of any real good straight line. There's several parameters you can tune here to make it more or less. You can see it didn't, this line right here, this wall or reflection right here, it didn't pick that out. There are parameters you can tune. I didn't put them on here. There are parameters you can tune the ransack algorithm to make it more or less sensitive. How big a wall do you want to pick out? How long, how flat the surface have to be? How many points do you look at? How many combinations do you want to try? You tune all those to your environment and make it more or less selective. In general, you don't want to find it. You don't want to be too picky. You want to find the big things, find the walls, and move on.
Could you use your robot diameter as your lower limit of that?
Well, so what you do, once you build those walls.
Right. But what I'm saying is, when you, at the beginning of this routine, could you put that in as once you're within this, I don't care anymore, we're gonna call that a straight line because my 2 feet is all that matters. That's, or my foot.
You could, yeah.
That would make it faster and.
Yeah, you could, but, so you could actually use some of the spike algorithm first too. Use the inverse of spike, eliminate all the things that have really big spikes, so you know those aren't going to be straight lines, and kick those out. Give you fewer points to look through. Okay. So here's the downside of ransack, or the downside, the other issue to deal with. The extended Kalman filter algorithm is we're going to look at it once a single landmarks be represented as a single point. Lines are not single points. So you can do 2 things. You can modify the EKF to understand whole lines as obstacles, not just single points. So for the reference point, as you're triangulating back, where do you triangulate from? Well, a single point's the easiest thing to triangulate from. So what you do is you find a long line, a wall. You need to convert that into a reference point. The easiest thing to do is back to your old coordinate system. Define a point perpendicular to the wall, perpendicular to the landmark, but through the origin, the world coordinate system origin. That way it's consistent no matter where you are in the world, that perpendicular line will always be the same. And that makes the math of the EKF easier later. You don't have to, you could modify the EKF to deal with the whole wall, but it's more complicated. So you find the wall, and then you find the reference point, your identifiable handle for the wall, and that's what you actually call your line. When you build the map still has the full wall in it with your state space added to it. But your reference point is that spot on. All right, next one is data association. So the data association issue is matching the landmarks you used to have with the landmarks you just seen, and understand what's new and what's old, what should go away, and what should go in. So you might not re-observe the landmark every step, every time step. Somebody may walk in front of it. You may get something that occludes it. You may walk around a corner and it occludes some of your old. You may walk away out of sensor range of the landmark. So you might not see it. You might observe something as being a landmark, but you never see it again. Somebody's carrying a big sign down the hallway. You pick it up as a landmark because it's big and flat and it's on a wall, but then it goes away. You also might wrongly associate a landmark to a previously seen landmark. Right. So all these are potential problems you run into in data association. A real full-featured implementation would take these things into account. I'm not going to talk too much about them because they're kind of in the minutia of the implementation, not really about the algorithm. But be sure those, if you work with those, that you're dealing with it. All right, so here's a policy that you can implement, though, that deals with those issues. We're going to assume we have a database. And I put that in quotes because I don't mean you got Oracle running on a 12-core server or somewhere back in your data center attached to this robot. What you really need to be able to do is keep a list of information about each landmark, attributes about the landmark, that you can very quickly retrieve. So you want to be able to look up things by, tell me the landmarks that are closest to this position, or tell me landmarks that look like this. So various questions you want to ask. So the database in this term is just a way to rapidly look through a list of things and pull back the ones you want. The other thing we're gonna assume is that we are not going to consider a landmark, and put it in the officially sanctioned landmark in our database until we've seen it at least n number of times in the to-be frame, in maybe 100 or 1,000 or twice, depending upon your standards. So I see one thing once, I'm gonna know it's out there, but I'm not gonna call it a landmark yet. I see it on 100 consecutive 100 millisecond time translations. Okay, it's there, it's kind of in the same spot, it's not moving, it's a good landmark. I'm gonna mark that down in my database as something I have to use. And that takes some of these transient ins and outs out of the environment. What you do is you do this nearest neighbor approach. 2 measurements of a landmark, we've already said the world we live in is noisy. You're not going to get the same XYZ point or XY point on a landmark time after time. So you query your data, you get a new landmark from your sensors, you know where it is in the world coordinate system. You now need to look in the database for the landmark that is closest to that in your database. And you have some threshold. So you find the one that's closest, and the one that's closest to where you're seeing it, as long as it's within some delta, right? Whatever your error is, I'm saying as long as it's within a meter of where I think it is, then I'm going to call that, I'm going to match those 2 up. Okay. Again, why you run into problems if you have so many landmarks so close together, you got to be very precise about which one you want, and you get confused. So, but that's how you do this. So you look at, take each landmark you discover in this path, so you look in your database to find the closest one that is that landmark, and you say those are the same, if it's close enough. And then you pass each of these pairs of associations, the extracted landmark, the landmark in your database through your validation unit, which is it the same shape? There's a lot of things your sensor could bring back. Metadata you can keep about the landmark if you choose to. And you can compare them, and you want to have this validation gate that's just, yeah, it's close enough, it's the same shape, same height, whatever. I've seen it long enough, and then you say those are the same, you match them.
And that's another reason why they use odometry as well, because a lot of times when you take a lot of this data, especially when you're using another approach, all these, using straight lines to match and grid everything becomes a box or a square, and it's just the mouth dimension of it. How wide is it versus this other one? So if you have things that are very close or similar to each other, like he's talking about, a bunch of pillars of the same size, a lot of them, then rope can get lost. So then you can use odometry to back it up. Say, okay, well, according to my odometry, I should be within this region. And it, like I said, even odometry, because of the error in it, can also be a factor. It can be, instead of being here, you could actually be over here if there's numerous objects like in a grid.
This is an area where we put a lot of additional AI in, and if you really, if the matching really is a complicated problem for you, there are AI categorizers, fuzzy matchers.
A lot of times too, like the stuff that I do is like instead of relying only on laser data, I was taking image data. So you do things like machine learning, where you're actually taking scene origin. So you're actually dictating, okay, well, what is this? This looks like it's a car. This is a tree. So then when you start labeling these things in this RGB world, then you can give like an evaluation on the origin, like where you are facing it. Then you can start adding these within the coordinate frame as well. And that's another thing another layer you can put on top of it helps you. So this is a good approach, but like you're saying, it is open to error. So there's other approaches on top of it, which is nice about it because you can continue to layer it just like you would in other systems. You can make it more, you can kind of tune it.
You can understand what are your landmarks, what is the information your sensor's giving you, and how do you use that information to correlate observations data.
So like in a sense, if you had machine vision and you saw a person, they could actually recognize people early, so you can just say, okay, that's a person, I'm going to correlate that into the data set. And so it's gone immediately. And there's other, like I said, there's other ways you can approach it, but.
I was thinking as a human traveling from like here to Kansas or something, I don't always know my actual odometry, but I know that I'm traveling X speed for X amount of time, which is roughly where I'm gonna be between here and there.
Mhm.
And I guess if I'm traveling slower and like a robot might be, that time speed might be. Your odometer, you gotta work enough to estimate your speed, but you're,
Yeah, it's all relative, right? It's like in the middle of Missouri, you really don't care how far away you are from Kansas City. When you hit Blue Springs, you might start to care, right? So you might, you can do that in. Humans get lazy, so they like to daydream off in the middle of Kansas or in the middle of Missouri. Robots have nothing to do but run those cycles. Those clocks are gonna run anyway. You might as well have them doing all the work every time. One of the things we talked about the flying robot is if you look online about quad rotor fails, about half of them seem to be bird attacks, where a hawk or an eagle will come down and grab it as prey and destroy it. That'd be a cool thing to be able to get out of the way of. I saw another video the other day on quads where actually I forget what country it was or what group it was, but a government agency was training hawks.
I think it's Norway or Netherlands.
I think it was Netherlands. They're
Yeah.
training hawks to go out and take down drones. Well, nothing I would like better than to take down their hawk. So if I see the hawk coming, I spin around, I fire a missile at it.
Well,
that drone with lawnmower blades.
Or be able to get out of the way, right? Because
Peter would be on your ass.
Drone dog fight.
Well,
Can you
it's all about
imagine
sensors and reaction time, right? So if you can, hawks are really good, but they're good at coming down on stuff. So you
But
can
they also
outline the
come
hawk.
down at 186 miles an hour per
Yeah.
paragraph, so the speed of closure is now became
It's a tough
a
problem.
real situation.
I said I would like to, I didn't think it would probably happen, but
You can use high frame rate cameras, but then again, the amount of computation on a drone
Yeah.
would be expensive.
It's that
so
thing.
Power consumption would be an issue.
yeah, it's that how fast, because the drone doesn't respond instantly.
And then you could
recognize,
do
know,
things like you
replan.
could turn all, you could do the processes on the server on the ground, computing just the live feed, but even then the latency between the robot and the computer would be an issue. I mean, birds of course, I know, I chase them with my
Yeah.
racing quad,
Yeah.
and they're fast.
They're
I
very
can't
fast
catch them.
and very maneuverable.
And that's me, plotting it, and I'm pretty good at
Yeah.
flying.
Just
so-
a-
First
Are
person
the
viewers?
hawks-
or-
No, well, I can't use first person because there's a limited field of view. So when I'm chasing birds, I turn my headset off and I just try to chase. You know,
Are the
but
hawks
they're-
attacking from the top?
They get the top. I
I mean,
mean,
so they're hitting the blades and everything.
yeah.
That's what I'm
Hawks
saying,
don't care.
lawnmower blades for propellers.
Yeah.
They do it once.
Yeah. Electrify it, put a taser on it.
Them robots, those spinning heads, you know.
The only thing you would need to do, and I could do with my quad rotor, is spherical. You know what I'm saying? So even if the bird got it, would just bounce off it like a ball.
Yeah, give it nowhere to hook, right? Because that's
Right.
what the
Yeah.
drone's very easy for it to get its claws onto
So
something.
if you had like a frame around it, if it was, you know, porous enough that you could keep the thing up, then it would just bounce off it. Or, the bird would push it around, but he'd get bored. You know, he'd be like, oh, I can't grab this, I'm over it.
Yes.
And eventually it would learn, and then eventually the birds after that would know, oh, don't even mess with those things. And you know, they're not even gonna come down, so you wouldn't even have be an issue anymore. You're training the birds.
So last thing is, so we did the matching process. We decided there's nothing that matches. You then put that new landmark as a new landmark in the database, and you mark the number of times you've seen it as one. If you continue to see it time after time after time until you hit your threshold, eventually you'll mark it in the database as a legitimate landmark, and it kind of goes into the comparison for everything else. So there's really two comparisons going on here. Does the landmark I found match an existing known landmark? If it does, you continue to match it, you increment the number of times it can see. If it doesn't, then you say, does it match a landmark that I've seen before, but I don't consider to be valid yet? If it matches one of those, then you increment its number. If that number goes over your threshold, you kind of move it logically into now this is a legitimate landmark set. Otherwise, you add the new landmark to the database and put as kind of the one and continue to march.
I'm curious about this. Maybe you're going to cover it in a future slide, but so the big question is, you're marking these landmarks and now you move, so now the landmarks have moved. How do you know it's still the same landmark, just in a new location?
That's why your coordinates that you keep in your database, you move it back to the world coordinate system. So if you're in a certain spot and you measure that landmark relative to you convert it, its XY position you store in the database is relative to your world coordinate system or the door or wherever I decide. I move and I rotate, and I find that landmark in a different position relative to me, my local coordinate system. But when I convert it back to the world coordinate system, it's still in the same spot.
So you have to have some odometry with the landmarks to know it moved also. You can't just read the
You have
landmark.
to know, right, so you take the Kalman filter that you did before, you know where the Kalman filter holds your best estimate of where you are in position, and you use that then to rotate that back. You're right, it's a noisy measurement. So it's not always gonna go back and overlay perfectly, but when you find the nearest neighbor, assuming you've got a relatively sparse set of landmarks, when you match landmarks up, it's gonna be the closest that matches your parameters.
Yeah,
If it's off by 3 feet, it's probably not the same landmark. If it's off by 6 inches or a foot, probably is.
Or it's moving.
Or it's moving, right? Which is, okay, that's where some of the moving objects, the ransack algorithm gets rid of a lot of those moving things. Or you haven't seen it but once. If it moves, I'll see it here, but I've only seen it once. Next time it moved to here, when I go back through and look, I've only seen that one once, I'll never consider that again. This one I've seen once, I'll never consider it again. That one's I've seen once, I'll never consider it. So a moving object through your field, because you don't see it in the same space often enough, will never really become marked as a usable landmark. And that's how it eliminates people walking in front of you, and another way it eliminates transient things. It doesn't use them as landmarks.
Another thing too, like if you had both algorithms like the spike algorithm and this other algorithm, you can use a spike as a determinant. Something large like a car, you understand, you kind of grab that identity of like how big it is, and you understand the motion of it, so you just make an approximation of where it might be later on in the future. Then you can use that in packing.
And this is where it says there's a lot of things you can do with these, depending on what your robot really is intending to do. Ours that we're modeling up here is simple.
Most of this SLAM is usually for like indoors, because everything is kind of square and it works really well. And usually rooms aren't the same size. There's
Well, the laser scanning, the ransack algorithm is indoor. SLAM can be either way, because SLAM is just taking the
that's what I mean.
inputs,
Right.
the landmarks, whatever landmarks you've identified, and using those to correlate your position. But the landmark identification is different indoors and outdoors, like we said. The sensors are different, the approach is different.
The good thing about being outside is everything is so big and so expansive.
Right.
It's open to approximation, so you can be off by a lot.
Right. And if you're out in a great open field, you're driving through, there is no landmark identification.
Like a desert.
You have to use your approximation as your odometry only.
Right.
That's the only thing you've got, but you've got your odometry. As soon as you start to find some more landmarks, now the Kalman filter will start to interpret those landmarks in the calculation and use it too. So
Like if you're in a desert and you're moving and slow, right? You're just checking the mountains. How big are they? Are they getting closer? And after a certain period of time, you'll start seeing some difference.
And so back to this thing, so you have this arrow ellipse you draw around the landmark, and the mathematics of it's here. I'm not going to go too much into it, but basically the database stores the landmarks. You know the error probability of that landmark, so you keep in the database all the different spots you've seen that, and you develop this uncertainty cloud around where it is. The density of the cloud is going to be most dense where you see the most readings, which is probably where the thing really is. And so, more math can be applied here that I'm talking about, but and in fact, you could have your own SLAM algorithm, or not SLAM, but your own Kalman filter that's doing nothing but evaluating the position of all of your landmarks if you want to. Okay. Finally, the last part, the next part, is the extended Kalman filter. This is the magic of this whole thing. So it's used to estimate the state, which is, in our case, position, but the state's a variable thing: position, velocity, orientation, any acceleration, anything that you want to call your state, you can. Most of the time in robots, the state is the X and Y position, the angle relative to the world coordinate system, and then very often you also keep the X and Y and rotation accelerations as the state. All right, so here's what the Kalman filter, here's the official Wikipedia definition of the Kalman filter. It gives a bound on the uncertainty of the observation, is really what the Kalman filter does. Sometimes it's also called the LQE, a linear quadratic estimation. But this is an algorithm that takes a series of measurements observed over time, and it contains statistical noise, which means we can model the noise as a statistical distribution. The assumption for the Kalman filter, and I'm going to distinguish briefly the Kalman from the extended Kalman because they're slight differences, and I'll tell you what those are in a second. But the Kalman filter assumes that the noise distribution is Gaussian. Everybody knows what a normal distribution looks like, right? A normal distribution is a form of Gaussian, Gaussian distribution. Right? Bell-shaped, right? So it's a normal distribution is a mean of 0 and a standard deviation of 1. That's a normal. Gaussian distribution is that same shape, but can be different means, different standard deviations. Gaussian is a more general term for a normal distribution. But what it assumes is your noise isn't biased. You don't have, I'll show you the diagram in a second. So the statistical noise and inaccuracies produces an estimate of unknown variables that tend to be more precise than those based on a single measurement. It does this by what's called Bayesian inference. Bayesian math is statistics. It's the probability of X given Y is really what a Bayesian distribution is. So what's the probability of this being 17 feet given given the random error I get for this section? An example of a Bayesian distribution. And it does that for each time. That's the official distribution. So what does it mean by extended Kalman filter? The Kalman filter is a linear model, which means it assumes that the distributions of all the noise and all the and your equations of motion are all linear. Linear means you add, subtract, you can multiply and divide, but nothing raised to the power of into 1. No sines, no cosines in the math, none of that. Those are all nonlinear elements. So the extended Kalman filter, well, the world's not linear. Right? You always do a linear approximation as your first order approximation because it's easy. The math is very easy. The world is not linear in most situations. You're very lucky if you never find a situation that would be accurate. So what the extended Kalman filter does is takes a inherently nonlinear system and linearizes it and then runs that linear local model through the Kalman filter, or through the math. It does this by, and I'm not going to talk a lot about this because it's sort of heavy calculus and stuff, but the libraries that you get to use will should already do this now for you. But it uses a Taylor series expansion of your nonlinear system. So if you're familiar with the math, you can take a nonlinear system and approximate it as a Taylor series expansion. F of x plus f of x squared plus f of x cubed, to some random length that makes it look almost exactly like any, if you go out enough terms, it looks like exactly the nonlinear function. Well, what you find is at some point, those terms that get higher and higher and higher become such a small variation in the change in the math that they don't matter anymore. And so you use the first couple of terms of the Taylor series expansion, and then you use a mathematical technique, a calculus technique called the Jacobian. How many people here do not know much about calculus? A couple of you. Okay, I'll talk to everybody else because I'll explain. So you have a curve, right? The first derivative is the slope of the line on that curve at any given point. If you've got, it's a two-dimensional curve. If it's three-dimensional, you have the slope of the line in the x direction, the slope of the line in the y direction, and the z direction. Those are called partial derivatives. The Jacobian is a matrix of all the partial derivatives around the primary axis of your system. So the Jacobian for this is what's the shape of your noise curve in the x direction, the slope in the y direction, the slope in the z direction. It uses that Taylor series expansion to model the curve, and then those partial derivatives in each of the primary axes to come up with a local linear system. then it applies these common filter to that local, as a local linear system. Because when you're really close to the peak, here, it's almost flat. And so that's what the extended Kalman does, is it adds this Taylor series expansion and the Jacobian to the calculations. So I'm not going to talk a lot about those. Advanced math and the libraries, if you use the libraries, are going to do it for you. But you should know at least the difference of what they're doing on this. And it'd probably be another day just talking about them. So the values out of this outside. Okay. So the motion and observation model are linear. In robotics, your control equations look like these first two equations up here. Now, when I see X and U and epsilon, all of these are matrices. They're not individual values. So X of t is the state vector at time t. Position, X position, Y position, rotation, X velocity, Y velocity, rotational velocity. So that's what when I say X, it's really a matrix of some kind. And we'll talk more about what that dimensionality is in a second. So the state at time t is the state at time t minus 1, your previous state, times this A matrix. This A matrix you choose. Choose is a bad word. You define, you build. The A matrix is the equations of motion for your system. So if you know position and velocity and delta t, you can use the A matrix, gives you your x equals x0 plus at squared equation, right? That's really what's built into that matrix. So the A matrix is if you don't change any of the control parameters, what does your robot do? If your control parameters are the velocity of the wheels, you rotate the wheel to a certain velocity. If I don't change any of those, how far does the robot move forward? The A matrix is what controls that. So it's about the radius of the wheel and the voltage you're applied or whatever you're controlling the wheel with. That's what the A matrix is. So the new state is the old state plus, if I don't change anything, where does it go? The B matrix is given U of t, which is new control inputs, given I'm telling the wheels to accelerate, how does that add or subtract from my velocity? Okay. Epsilon, the last term, is the error. And that's what I don't know, but that's that matrix of the distribution of the errors. And they'll talk more about how that comes in a little bit later. Z is the observation model. So the first one is your odometry equation. The second one is your sensor feedback equation. So what you're saying is that the state of the observations at time t is the state of the observation, is the state at this time, times this C matrix, this other matrix, plus the errors in the observation, plus or minus observation. So basically it's saying, given the state of the world, what should I observe? Where do I expect all the landmarks to be? Is what the second, the Z of t. Now I take my sensor inputs and I bring those in against the Z of t, and I say, I expect my landmarks to be in these spots. They're really in these spots. There's errors. Use that to figure out my position. This is where a lot of complication comes in, a lot of deep math. There's a really good YouTube video, series of videos from a group called I Lecture Online. And I would really recommend, it's 48 videos. They run anywhere from 10 minutes to 40 minutes. But it's a very, very good description of using the Kalman filter to step through robotics control problems. And if you're interested in how all the math works for this, the guy does an excellent job of taking you through step-by-step and examples and really relevant stuff. So go to YouTube, you do a search for special topics, the Kalman filter. You'll find it. I highly recommend it. All right, let's talk about what some of these pieces are. So this X matrix, the system state, is the position of the robot, X, Y, Z, and theta, or X, Y, and theta. and the position of each landmark all put into a matrix. One column wide, it's 3 plus 2 times n high, which is n is the number of landmarks you see. So first iteration out the gate, it's a 3 by 2 matrix, or sorry, 3 by 1 matrix, one column, 1 by 3 matrix. Right, so it's x, y, x position of the robot, y position of the robot, and theta of the robot in world coordinates. As you start to find landmarks, you add the positions of those landmarks, the states of those landmarks onto this to where your best belief is. The next important concept, and we're going to spend a couple of slides on this because it's important to understand this as far as how it deals with the error terms. You build into your matrices these error terms, a thing called the covariance. The covariance matrix is a measure of how strongly two variables correlate. A covariance of 1 means they track exactly the same way in exactly the same direction. The covariance of 0 means move 1 and it doesn't affect the other one at all. Covariance of -1 means you move 1 up and it only moves down, equal amounts. Okay? So what you do in the Kalman filter is you build up these huge matrices of how a change in one thing affects a change in the other. And this is over all of your time periods. So each of these, look on the left here, we have the x and y positions over time. So each of these is a different one of your time steps. Each row is a different time step. And you've measured the x and y position of that. So to build a covariance matrix, you find the average of the x's and the average of the y's. That's on the left over there. So 4.89 is the average x value, 5.44 is the average y value. And then you put that into the equation up at the top. N is the number of samples that you're looking at. You can look back however many samples you want. You don't have to look back to time 0. You can look back the last 100 samples, the last 1,000 samples, whatever you want to do. But it's 1 over the number of samples minus 1 times the summation of each x minus the average times each y minus the average. Okay? And so that's the definition of covariance. So you not going to a lot of the detail of the math behind it. You go through and figure that up for each one, for each cell. I didn't put it in. And that's going to go into this matrix I'm going to show you next slide. Now, you have to initialize the covariance matrix. I probably should have put the slide later.
Is that a landmark?
That's for everything. So let me show you the matrix here. So this is the covariance matrix. That is a slide I should have had later. You got out of order. So the covariance matrix starts out as a 3 by 3 submatrix. 3 by 3 is the x position, the y position, and the theta of the robot. The rows and columns are the same thing. But where they line up is the covariance. How much does affecting one affect the other? So the spot right here, this spot right here, would be given a change in the x position of the robot, how much does that change the orientation of the robot? Yeah, probably 0, but not always. Because of the noise, sometimes you'll hit a bump, and moving an x bumps theta because of a slip, or because you hit a pencil or something on the floor. So theoretically, mathematically, if you were the frictionless, the massless elephant in a frictionless plane, that would be 0. Real world, that's a real number. Okay, so you can figure that out, put that in there. You can do it experimentally, you can do it mathematically, you can guess, and then you can put other algorithms on top of here that can update that, because actually that'll update as time goes on. And then what I put below here is LM is the landmark. So x position of the landmark, y position of the landmark 1, 2, and 3 for each position. Okay. So the robot position covariance matrix is this 3 by 3 matrix. When no landmarks are out there, that's all you got. You did also have these covariant landmarks, the covariance of the landmarks, which are 2 by 2s, because you're not keeping theta for the landmarks. But this is showing how do changes in landmark 1's x position, how do they correlate with x2? Because of noise in the system, right, they're going to vary back and forth, even though physically they're fixed. What we're reading is we're building that point level, building that distribution up mathematically, time slice after time slice. We're figuring out the noise that I'm seeing in these sensor measurements, how they're coming back, and sort of how one is changing relative to the other.
Like on your, you got a left and a right. You'd say one of them might be your odometry and the other one might be your scanner.
The same thing.
Same thing.
So what this is really saying is, how does the Y position of landmark 1 change relative to the X position of landmark 1?
I was wondering if it was Y against Y horizontal versus Y
So
against vertical.
this is all about where you, so in this case, since these are landmarks, so all this landmark data is coming back from your sensors. Right? So as you read the position of the sensors and you convert them into world coordinate systems, time after time, you're seeing how those things vary based on that equation. So each time you get an X and Y position for landmark 1, you add another line down here, another row of this data set, and you figure the covariance of that change, right? And then you put it in the appropriate cell.
It's just a weighted measurement over time.
So it's kind of like how much the landmark 1 changes
How much noise is there really in your
every time
system?
you read it.
Yeah, because if you've got perfect readings, if it were a perfectly academic, high college physics exam, the covariance would be 0. You would get an accurate reading of 4.7 meters every time. And so the covariance would be 0. But what you're really saying is how much distribution, when do I see it here and when there and when out? That assumes, the Collin filter assumes that's a Gaussian distribution, that you'll see outliers a lot less often and you'll see things closer to the real value. The nonlinearity thing, the Cindy Collin filter says, I'll just take that, I'll nonlinearize that. But, so that's what this is capturing, is how much of that noise as I read these things, sensor to sensor, time loop to time loop, build up those distributions of the error that I'm reading in the measurements, right? And that's what goes in these matrices.
That's why it's so important for resolution when you're talking about sensor data, because after you do all the an estimation, the more estimation you do, the lower resolution. So if you already have sensors with full resolution, it's going to even be worse at the end. So you need something with high resolution, extremely high resolution.
Well, you do and you don't, right? Because since if it models out as a Gaussian distribution, even if you have a wide variance, you've got a lot of noise in that data. When you take lots of readings, if it's truly a Gaussian distribution, the readings are going to start to average toward the real value.
But I mean, that'll work in a model environment, but I mean, eventually, like I said,
Everything will fail at some point,
Yeah.
right? But if it's so noisy, the distribution is 25 feet, well, that's, you're going to be able to estimate within a foot, but that might not be good enough, or it might be fine. If your variance is 2 feet, that you get noise within, you can probably estimate it at half an inch. So it's a trade-off, but the idea is that nothing's perfect, but you can get this good enough. We used to joke with an engineering approximation. It needs to be good enough that you can't tell that it's wrong.
Yeah, the broad side of the bar.
that's why it's excellent
depending
that
on
he's
what you're
giving
trying
us
to
talks
get.
on all of these things, so that you understand, the limits of each individual algorithm, so you can better suit, to whatever model that you're trying to achieve.
And when we're looking at our robots now, or remember like the military, the missiles fires a shotgun shell at the last second, it's almost all there in the aircraft.
Right.
The dispersing like pattern of projectiles for this exact reason.
Make it
How close can we get? We just need to get within this range of these metal darts, and we're gonna get you.
Right. And that's the same thing, right? You got to be close enough that you can't tell it wrong. And that's what this thing does.
Yeah, it's meant to do that.
Yeah. So the last piece of this is the covariance between the robot state and each landmark. So as I move the robot around, how is that varying my measurements from the different landmarks going here? So the more landmarks you have, the more covariance matrices, more cells you got to go back and calculate. Mathematically, it's a lot of calculations, but it's a very simple math. But again, it takes time. So a robot that's moving at 100 miles an hour, flying, trying to chase down a hawk, is, you're trying to say to recycle. A robot that's moving through here at 2 miles an hour, you got plenty of time to do this. Right? This is 20, 30 milliseconds.
And something else like that math you did, I have this phrase I use, consistently wrong. Like sometimes tank levels are wrong, like a lot wrong, but it's consistent. And if the guy is happy with this level and it'll say that every time it gets to here, that's good enough. It don't have to be the right number, it just has to be consistent.
That's right, exactly.
You're detecting a change more than the actual reading.
Yeah, the distribution, right? So you know it's gonna be within here, and the Kalman filter uses all those distributions, kind of overlay each other, so that the means tend to spike way up high. Right? And when all these means of all this noise tend to add together, it tends to give you the right answer. Versus in each individual, when it's so noisy, you really can't tell if it's here. And that's kind of what's behind this Party's covariance things. The last piece is the covariance between each landmark. You know, how much the landmarks move relative to each other as I take my samples. You build all that matrix up, and then you throw that into a calculation that gives you what's called a Kalman gain. And this is the magic number. This is the money shot. The Kalman gain is the error in the estimate divided by the error in the estimate plus the error in the measurement. In our case, we're describing here, the estimate is, in big of either one, we would call the estimate the odometry. Right? Where am I estimating I'm going to begin? The measurement is our sensor triangulation back to our spot. So what this is going to say is the Kalman gain is my estimated error divided by the estimated error plus the measured error. If the estimated error if the measured error is very low, this term goes to about 0, which means you've got pretty much estimated error over estimated error, which is about 1. The Kalman gain is about 1. That's telling you trust the estimated value the most. If the measured error is very high, if the measured error is very high, then this becomes the dominant mathematical feature. The Kalman gain becomes close to 0 if say and trust the other one more. So the Kalman gain gives you a mathematical position between estimate and measurement to say, here's how much to treat each one for each of those parameters.
And it's going to be a percentage every time.
What percentage every time? The number between 0 and 1. 0 and 100, yeah, or whatever, 0, yeah, a percentage number. It'll never be 100, it'll never be 0, but it's 0, sort of open bracket, 0 to 100. And so for each of the parameters you've got, in our case, x position, y position, theta, x, y, z, x, y of all the different landmarks and everything, it tells you how much of each position, how much of each component should you trust. And you do a weighted average and say if my estimate says I'm here and my measurement says I'm here, I'm going to weight that position accordingly and put me somewhere in the middle. This is where we're using that innovation term again, and I complained about earlier. So in this matrix, this Kalman gain matrix, the first column describes how much gain should be for the innovation in terms of range. So in this case, it's range and bearing that are my 2 parameters I'm measuring. So what's the gain in range for each of the parameters? The second column is how much should be gained from the innovation in terms of bearing. So it's just saying if each of these are their own common gain values. So you do each one, because you may be very accurate in terms of range, but you stink at bearing. And so you want to use one value predominantly for the range and a different value for the bearing. Okay. And this will figure that out over time. And adjust even as you go in different environments. And maybe different environments, the percentage changes a lot. Maybe in certain environments, the range is going to be really good, or the sensors are going to be really good. In another environment, you got to like out in open, right? If you go out in an open field and you get almost no landmarks, you're going to have to deal with your estimates because you have no measures. When you come into an environment, you have to pick up some measures. Now you can build, you want to sort of bias them more towards the measures because they're more likely more accurate in some situations. All right, back to our 3 steps, and we're almost done. Back to those 3 steps of what the what the SLAM algorithm does. So first thing we're going to do is update the current state using the odometry data. So it's really a predictor corrector model. You use that one matrix out matrix that I showed, and say, given where I'm at, I want to predict that I'm at this new spot, which is my velocities and accelerations and delta t, say I should be here. So you update that position, then you want to update the covariance matrix. And then step 2, update the state from the reobserved landmark. So you want to grab your sensor data and you update your state. You look to see, the first step was predict where I should be. This is triangulate back from all my landmarks as to where my landmarks tell me I should be. So you reobserve every landmark you've seen enough times, you reobserve, you predict where the landmark is using your current estimated position, your estimate position. You predict where those landmarks are, and this is the formula you use to get that range and bearing to your landmarks. You convert those back to world coordinate system coordinates. You do a bunch of complicated math that I'm going to ignore because that's where all that Jacobian matrix and nonlinearization, the Taylor series expansion, that all happens in there. Feel free to go look at that. That YouTube video will talk a lot about that in a couple of its sections. Really good. Step 2 is the big steps. Those are a couple of slides. Now you can compute the Kalman gain, right? And this is also called the innovation covariance. This is the matrix, this top formula here, matrix version of the thing I drew. Right? So this is what you would do mathematically with the matrices. H matrices are really just there to transform things into the right number of rows and columns. If you look at that video, he'll explain that a lot. All that complicated math, it really is saying the same thing as the Kalman filter. The Kalman gain is the estimate divided by the estimate plus the measure. That's what that thing on top comes down to. That Kalman set now contains a set of numbers indicating how much of each landmark position and the robot position should be updated according to the reobserved landmarks. So that matrix I showed, that two-dimensional matrix, all the Kalman filters on it, that's what the output of that equation is. Once you've got that, now you've got an observed or an estimated position and a sensor position, and you've got the Kalman gain to tell you how much of each to believe for each of the measurements. So you compute a new state vector using the Kalman gain, which is that X state matrix we've been talking about, the XY positions, the theta, all those things, of all the and of all the landmarks, equals the old one plus the Kalman gain times the difference of the two positions, the observed and the measured positions. And then you go back and you add the new landmarks to the current state. So you build out your covariance matrix with landmarks you don't see anymore because you've moved on, or new landmarks you've seen. You go back in and readjust your matrix to add those new values. And we're done. Robots now ready to move again, or really take another time set, not to move, but take another time slice, do all this thing again, observe the landmarks, reassociate, update the system state, and then add new landmarks all over again every time. So thank you for your attention. I was only about 15 minutes longer than I wanted, which is better than I thought I was going to end up. But hope it was helpful. Any questions or anything anybody wants to finish up with?
So this software basically is going to tell you the correction between the observed position and the calculated odometry.
Yes.
Yeah, but it's gonna update it every time.
Every time, it's dynamic.
It's gonna say,
And it's
this is becoming this, and this one is like this.
Yeah.
We can trust that's closer, so we can use that.
Is this going to bog down the system if somebody puts his foot out in front and stops a robot when he's moving? Is all the mathematics going to crunch to a stop? Or
No,
what? I mean,
no, because because if it stops, let's say that happens, they put their foot down in front of it, or
yeah, the
stop
wheels
it,
are spinning.
and the
He
wheels
thinks
are
he's
spinning.
moving.
What it's going to realize is it's looking out at the world and saying,
Nothing.
my odometry is telling me I'm moving, my world's telling me I'm not.
I see.
The Kalman filter will then start to believe the world because it's going to become a more dominant piece. pick your foot up, let the robot move again, and it's gonna start to then rebalance and go, okay, I'm gonna trust my odometry more and more and more, right? Based on what it is until it finally over, sort of, because you're not going back to time equals zero with that summarization. You're doing the last 1,000, the last 10 seconds or something, the last 60 seconds.
And this is just his algorithm, like in Ross, they have other things like obstacle avoidance that's built into the platform navigation. So if you get errors like that, then it looks up because it says, okay, if there's a, this much error, then we're gonna wait. And then it has the two states. You can say, okay, we're gonna wait for this thing to move, we're gonna continue to move, or we're gonna try to reevaluate the localization because something happened.
So it is evaluating the accuracy
Well-
of the.
Well, this is, I'm talking about, this is ROS.
Let me qualify the more general terminology. This is a very specific self-contained algorithm for a specific state the robot's in. If you look at robot architecture as a bigger piece, there's several layers to it. Right? There's route planning, there's goal setting first. So what are you going to do? And then to accomplish that goal, there's another layer of route planning. How am I going to do it at the macro level and build up the waypoints in the direction? And then there's the goal execution, which is this. So how do I tell where I'm going from here to there? And then the very bottom is convert that point robot into my actual dynamics, a hopping robot or a two-wheeled robot or a snake. At this bottom layer, at the layer where this operates, there's a concept that most people use, like the name, it's a finite state machine. And so one of the things it's doing, personality, it's not personality, but the name like that people call it. But anyway, all of your sensors are running and you're in a variety of states. This is a state that you're in where you're moving to a goal and you're gathering information and keeping track of where you are. If somebody puts their foot in front of you, you have a sensor hopefully that detects that. You switch the state out of this into obstacle avoidance with a higher priority task. Once you've accomplished the obstacle avoidance, you've backed up, you've avoided the obstacle or whatever, and there's all kind of algorithms to do that specific task, and you're ready to continue your original mission, then you roll this thing back in and start using this again.
So this math is evaluating the reality. It's evaluating how successful you are at navigating around place to place. It's telling you, no, your wheels are slipping, or no, you're doing just fine.
Well, I would say it's telling you that as much as it's adapting to when that happens.
And it's determining where you're at. So it keeps you have your logistics through this. It's not obstacle avoidance. It's not telling you how to get to any point. It's just telling you this is where you are. This is what's around you.
Yes.
You still then have to use that.
Yes.
Use it as a tool too.
It's like
Decide
present
where
state.
To do all those things.
It's like present
Your
state.
Yeah.
And then
The current gain is for at that particular location, the current gain will indicate the robot to use which modality, is that correct? By the current gain number. Is that
And
correct?
it will tell you how much of each modality to use. It won't be binary. It won't say use this or use this. It'll say use 20% of this, because it's got some information that's valuable, but it's not completely accurate, and use 80% of this because it's more trustworthy. Right? Because both of them are inaccurate.
Waiting.
And it's just telling you how much of each one to trust.
I think it'd be similar to your feet and your eyes at nighttime. Like you're wanting to go to the hallway, go to the restroom, and you know it takes about 10 steps, we'll say.
Yeah.
And your eyes can see, but it's dark, so it's poor. So we have to say, well, 30% eyes trust,
Right.
50% legs,
Memory.
the other part being your hands, perhaps. And so you weight them, but then in the daytime, it's nice and bright, so maybe your eyes are 99% and your feet 1% or something.
So the way to corroborate these two sensor systems and come up with something usable.
Okay. And you can extend this. We talked about it, two sensors, right? The measurement sensor and the odometry sensor. You're not limited to two. You could have 3, 4, 5 different inputs. The downside is that covariance matrix, there was it becomes multidimensional. There's a dimension of that covariance matrix for every dimension of your control.
And so you're gonna have to have a more powerful processor.
Well, more memory, right? I mean,
Yeah.
it's all relative, right? So what, I used to, when I did robotics and machine vision, I was doing machine vision inspections on bottles that were flying by at 1,200 a minute. And I could take a picture, I could do a sonic flip off of them, process it, and tell whether the caps were on tight. right? And I could do that at 1,200 a minute. That was almost 20 years ago with machine vision. I had a frame grabber that could grab the image, have the image stored in memory there. I could do the same thing with my phone now because of computational power. You know, I said, don't underestimate how much power some things have. You can make anything run slow. Some things are complicated. It's all about balance, right? So if you're going at 2 miles an hour, you've got a lot more time to do things than if you're going at 100. Right?
Plus, you also have, if your sensor only operates at 10 hertz, your computer can do a lot
Right.
of playing around while you're waiting for the next that next input.
Yeah.
So if that's as often as you could update that.
It looks complicated, but I guess it does run a
Yeah.
little faster than this.
You know, microseconds of, running it, even a Raspberry Pi now, what, 3 is 1.2
1.2.
gigahertz, 1.4 gigahertz. A lot of clock cycles, right? I mean, it's, if you, and you can do things, right? You want to be real inventive. This is an algorithm that works very, very well with the GPU because it's a lot of parallel matrix calculations. You load these matrix up into a GPU and let it crank the things out as if it were graphics transformations. There's APIs that make it easy for you. Not every application is data parallel where you can do that. This is one where if you've got a lot of stuff going on, it can be very data parallel, and you can load those multi-dimensional, high-dimensional arrays up into the graphics unit and let it crank them as if they were putting up, pixels on a 3D object.
That's why a lot of the newer big companies are going away from GPUs because they're just making chips basically that are tailored for machine vision or certain applications. So they're going to be low processing computing units that you could have like a Titan X, which is a really very strong GPU. You could have a chip that's almost emulating that same because the architecture of the chip is so small and it doesn't need a lot of processing power.
The problem with the GPU is getting the data loaded into the GPU to start with.
Right. The memory is also an issue. So.
Memory, yeah, because you can get big memory GPU boxes, so 64 gig of GPU memory, but it's getting 64 gig loaded in there time after time. If you want to redo this matrix, every 100 milliseconds, you've got to get all that data reloaded to the GPU. Better if you've got a chip that can deal with it on the local bus.
Something I have, like map storage, so data size, that's the kind of a question. Like if I would take a video with my phone, the size, relatively speaking, it gets longer and longer. You got a gig for an hour maybe, I don't know. So for a map, and I don't know how to really size this, but would you liken it to a text file or would you liken it to a video file? In the size of time and
like moving a map, like doing the mapping algorithm, or
making the map and storing the map. Are you storing something nearly the size of a video?
No, you're storing it as it's stored a lot of different ways. Depending on what you're going to do. Assuming you're going to use the map you're building for route planning, the best way to do it for route planning is to store it as XY cells of some dimension. 6 inches, cells 6 inches. You break the room up into little 6-inch cells. 3-dimensionally, 6 inches by 6 inches, all of your cells. You would only store things that are actually in one of the 6-inch cells. And you can store that in what's called an octant map. So if you're familiar with databases, binary trees, right? So you've got the high values here and the low values here. An octant tree is, since the 3-dimensional environment, you've got from the cell you're at, you've got 8 surrounding cells. Those become the 8 branches off the node. So when you want to navigate that or store it, you're not storing whatever this room is, 40 feet, 86 inches, 80 by 80 by, whatever, a lot of cells. You're storing this tree. And so if it's an empty space, there's no node in the tree. But when you move from node to node, moving to node 1 is always moving up in the X direction or in the Z direction. Moving to node 2 is always moving this direction. And so you can always be very dense in storing that space and very quick to navigate because every time you take a hop, you knock off 7/8 of the width of what's happening.
And would it also be kind of like image compression where like one area is all black? So there's say here to here.
Yeah, I mean, it depends on what you're going to do with it, right? You got to understand what your mission is to know which of those algorithms to choose. just like in this, you have to know what environment you're gonna be in, and know what sensors to pick, and know how to interpret the sensor response.
And ROS, on a practical level, ROS stores maps as PNG files that are just black and white. When there's two files, there's an actual, PNG is just an image like a JPEG, and it's black and white. And then there's a second file that's a definition file, which is really short, that just says 1 pixel equals 1 centimeter or 1 pixel.
Dimensionality. And the reason they do
Yeah.
that is because they're only using like the Hector mapping, which is it's just a 2-dimensional map. Like if you go into like we're talking about normally like a 3-dimensional, so you have off mapping, which is the same component cloud generation we're using those trees in order to define space. Then it gets more complicated. But yeah, for typical mapping, just on the localized level, just 2-dimensional, use just like the G mapping, which is just basically Cartesian.
And you get a result of this algorithm cranking up to convert what you find into PNG format at a higher level that ROS is going to be
So, in a sense, you could have, just for layman's term, white pixels, there's nothing there. Black pixels is an object. Travel as much as you want in white, look out for the black.
That's the route planning, right? There's algorithms, depending on what your goal is. If it's just to go explore, yeah, travel wherever you don't have white or black is where you want to go. You know, you can travel in the white. This is what I said, building the state space. If you find something, you mark it black. You mark it black bigger around it because that way your point taking the out. But it's easier to manipulate the point dynamically around the room and expand all the objects so you don't want it.
I'd also like to note, I've started using, so anybody who's intimidated with the math, a lot of this stuff, you really don't have to know the math. They already have applications that do this. Like if you're using ROS, somebody's already written an extended common filter that you just have to feed your information into their filter and it spits out an answer of where you are. And just to note too that it works really well. I mean, practically, it's effective.
It actually corrects the multiple sensor systems and gives you a best map.
I started using it actually yesterday. I used somebody else's library who uses this technique. And yeah, I was having a lot of problems with my robot. It couldn't move very fast and it would drift. It would just think it was like floating up into space eventually. And by using the second sensor, and this is essentially fusing the two sensors together, it was incredibly accurate. I could now run at full speed, which my robot goes like 3 miles an hour.
You were also using a laser, an actual industrial laser now, so it's, the refresh rate is much quicker.
The quality of the sensors was higher too, but
Right.
Yeah, that's the thing is, you know, I say this thing's, you convert this fast, 4, 5, 6 iterations through this, you've got a very accurate estimate of where you are. If you're running at 10 hertz, less than a second, you've narrowed down to your accuracy spot. So it's not like you have to run for half an hour. You know, in computer terms, you know, you're 10 hertz, you're a second, you've got it. So before the robots really started to move, it knows where it is.
Most of the sensors are usually running like 50 hertz.
Yeah, 50 hertz, you know, a fraction of a second.
So it's 5 times faster than you necessarily need. And that's usually good because like the thing you're using it as a filter. So 5 times over, you have a pretty decent approximation.
For human traveling speeds, like 0 to 12, 15, you're within reach of 50 hertz probably.
Yeah. Oh, yeah, it's for robots, it becomes, anything becomes a problem when you're traveling on robots.
Yeah.
And with this, if you do run any computational problems with ground robots, just get you an Arduino or get you a Raspberry Pi that does nothing but this. And it sends its results continuing as a stream back to the mothership, the motherboard, right? It is this control of these higher level functions of route planning and obstacle avoidance and other things. You know, not obstacle avoidance, that needs to be over too, but things like route planning and goal beating. You know, that's a higher level function. It's a slower, you know, check every second if you make your goal, but you're running this thing at 10 hertz or 20 hertz or whatever you're running.
And there are there's already Arduino libraries for common filters.
Right.
We even tried to use it on our GPS, but it just.
Well, that's why I said at the beginning, I didn't want to try and make you have to code this, because it is complicated, heavy math, a lot of work. I wanted you to be able to understand when you use the libraries, what it's doing and what your inputs need to be, and what to expect out of the result.
And why to use it, in other words.
Right,
Apparently,
yeah, and why,
And
and
it's
why.
good to know, I mean, because now you have a better understanding of what the algorithm is doing, and then you know how
If you have a problem, you know where to look
Yeah.
to find a solution.
Yeah, not to go into debug their code. Yeah. Or like,
And as far as that speed versus capabilities, I was thinking that a guy driving a 747 airliner, he's making the assumption there's nothing in the middle of that cloud, two clouds ahead.
that's why they have
a
radar,
mile
right?
ahead.
That's why they have radar that reaches out to
Yeah.
miles, right? Because they got time to react to it.
Yeah, and our Formula One drivers assuming that over the top of this hill is always clear unless I see a flag telling me otherwise. So I'm gonna just keep it forward and
Yep, yeah.
blind or not, I'm just doing it.
Yeah, but we're doing this when we drive, right? Keep it in the
Yeah.
lane, as a common film.
Yeah.
You're never purposefully in the dead center of the lane. If you're in the dead center of the lane, it's an accident. You know, because there's always drift, but your eyes are estimating, you know, and making the best guess based on your tactile feel of the road, your visual senses, your experience, your vestibular system, you know, so what you're doing, you're taking all these things and adding together, put yourself in the middle of the road.
When you're wrong, you have the police officer come and tell you about.
Well, even like that, I know there's the Tesla car crashed a few months back, the first autonomous car that actually killed someone in it, and it wasn't a major error. And I think they have an estimation that it was because there was a truck that it didn't hit, and the truck was wide, so they blended into the background. At least that's their evaluation. It might be something other, it could be hardware, but
Yeah, this is obviously a lot of this is used in driverless cars.
Yeah.
So,
yeah, it's been, I mean, yeah, Google has incorporated it. Ross essentially started building a lot of these libraries with OpenCV, and they've just kind of branched out to industry almost everywhere. So
Quick question, not to get off topic, but was the driver or the passenger in the Tesla killed or the person it hit?
it was the person that was driving, or that was
In the
in the
Tesla.
Tesla.
And they're also trying to blame that he was watching his
DVR.
He
Yeah,
wasn't paying attention to.
he didn't even have his hands on the wheel, so he couldn't even.
Right, it wasn't even.
Well, the thing is, that there's like, they tell you, even when you inactivate that operation, that you're signing off, that it, you know, they're not at fault. It's
Like
the beta version, and then it's open, you know, to error
you
from
know, the
error.
highway to Nevada, not in.
A lot of people, they're actually debating it now, because a lot of people are actually abusing it, you know, they get in the back.
People do it.
Get in the back seat
Autopilot.
and record
People do it.
themselves while the car is driving them places, you know, and that's not what they intended it for. It was more of like, you know,
It's not as dangerous as a little car.
Yeah, it's like a cruise
People
control,
are
but-
doing it with non-autonomous cars right now, you know, they're.
Yeah, it's almost safer than you right?
It's the rule with pilots too, it's not a brand spanking new pilot. Some guy that's got 400 or 500 hours in his
They
dog.
trust the
They
system.
trust himself now, and then when it's 88 Japan, who said you don't have to fly it, then you.
Before we
Yeah,
get
I
off
wanna
topic,
say, before everyone goes, I appreciate his talk, and I wanna congratulate him.
that's all I wanted to say. I just wanted to make sure that we, thanks Craig for the
Yeah.
talk. That was
Does it
good.
help? I mean, it did at the right level, everybody.
Oh,
Yeah,
yeah,
that
he
was
did a
great.
very good
It was
job.
good, yeah.
Now, is there anything else, or are we gonna be doing any,
Um,
I guess I missed the beginning of it.
So we can do show and tell if anybody wants to show anything off. Hang out for a little bit.
Nick, did you want to show your project?
We are out of our formal agenda in this meeting here. We used to have office club announcement, followed by talk, followed by show and tell, followed by Q&A.
This is called ad hoc agenda.
Yeah,
So do people want
The last,
a
the
more?
last few times, someone just hijacked the whole meeting, and a lot of people left pissed off. I just want to give you feedback, so get a better time control.
okay.
Yeah.
And also
Yeah.
give priority to the speaker, don't hijack the speaker. Whoever the speaker is.
All right.
give
Does the speaker
an honor.
not have priority or?
There's a feedback from a few people, they don't talk,
I think he's, yeah, talking about previous meetings. Where
We do our
there were
respect,
side
I-
discussions.
You
and-
too, great contributor to the club, but I have to give you the feedback.
Oh, yeah, we appreciate it. Like I said, we're not perfect. And we're, a lot of the times, I mean, we're on strict
No, but it has to
schedules
be
ourselves.
a form of a fixed pattern which worked well in the past.
So are-
And you
is
didn't
everyone, I
follow it.
mean, does
And you didn't
everyone,
follow it.
does everyone,
Well,
have
we
that
decided
same-
not to have a strict pattern though. That was one of the changes.
One more
We, in the
thing.
past, we had a very strict pattern and we went to very non-strict. And now we're trying to be in the middle and be a little informal and relaxed, but have some kind of structure. So we're trying to get a middle ground here is what the effort is.
2 hours straight lecture, I think after 50 minutes, people lost interest, you know?
Do you think we?
I think it really depends on the presentation, like on Craig's presentation is extremely in-depth and there's no way.
Oh,
you can
sure,
cover it in
I'm
30
grateful,
minutes.
I'm grateful, I appreciate that, but.
Right, I
but
mean,
it's-
we
have a better
still
format.
kind of, I mean, we're, with our limited schedules, we're trying to, approach this the best way possible. If anyone else wants to help organize, with us, that's extremely appreciated. We're open to, I mean, this is everybody's group, this is not just our, this is everyone's here. So anybody's input is, taken in that context. I think
Just feedback, you know.
So how would you want to see the day different?
Today different, I would specify the talk no more than 1 hour.
Okay.
No more than an hour?
Either
No more than an hour.
that, or maybe have a 5-minute break after.
That would be good, yeah. That's our goal.
If
That's
2
our
hours
goal.
straight, I know this couple of people, last few times, Rich McDowell come here, he want to have a Q&A, ask a question. The entire 2 hours on Ross, and he was really pissed off.
And we're
And then
actually-
Vern left because he expected to come and learn something.
Right, and the thing is too, like, I think, originally the approach was, and I think we're coming back to it, because originally I was thinking with this group, robotics, because there's so many other groups that are already doing Arduino, that you could go almost anywhere, to any of these makers, and get that. And this robotics is more like, okay, we're trying to, get people more, if they're interested in robotics, we're giving them a very in-depth look at what robotics and what's happening today, and to keep you up to date. But I think we might go back to doing two, maybe if we can, fit two different presentations, like a basic, because I know everyone is not familiar with these things. So if we can kind of, and the problem is that we don't have a lot of time, right? It's like you're saying, in half an hour, how much can you really cover?
Can I clarify something on the last talk? Because I ran the last one, that's one you were talking about. That wasn't a presentation, that was a workshop. I was trying to do something different. Where it was really not me presenting, it was everybody kind of I was hoping to get a lot of participation, which I did get, like, 4 people brought their machines.
Maybe maybe a misunderstanding because people come here, they still have it in the old format that they want to have some, to see what's something to inspire them or to ask a question.
And I think a lot of that inspiration really comes, in my opinion, at least for me, is seeing other people bring in their project.
That's right.
When people bring in their show and tell is, I think, really key in this group, and I want to keep it that way. And I wanted to talk to Josh about it, if we can have the show and tell in the beginning, so people, because I know everyone, when they get here, they're inspired out, I'm here, I want to show my project, I want to see what people are doing. And then after that, a lot of people might not be interested in certain topics, so they could leave. They don't have to wait and stay the whole time and wait for the show and tell. So I think that's
Therefore, the speech should be more than 1 hour, and it should give time to some others. We are not coming here to learn theory. You just get some idea, like he said, then go home and study.
Right.
Look at YouTube and comment.
Or we could continue it at the Thursday night session or something.
Right.
I don't know.
Yeah.
Could there also be, I mean, it's really hard to come up with some of these, I know I've only been to 2, but is it group? It's hard to come up and go, okay, I've heard enough now. But it's not, if we had a clock that's going all the time and say, we got a half hour for this presentation. At the end of a half hour, you can say, I can do the other half on another meeting or something, and now, anyway, that clock is totally arbitrary, nobody has to take it personal. And just have it there and go, now we have the next 15 minutes we usually give to show and tell.
So have a timer run.
And just have a timer
I'm
running.
gonna disagree. I don't like the structure.
Well, I think the problem with it is not all ideas can be discussed in the same amount of time.
Yeah, I thought
Well,
this
I think maybe at the
but-
beginning of the meeting, you have to say, we expect this talk to go this long or something.
The other problem is
But
too, you have to
timers is a little
understand,
tough.
there's a lot of people participating.
Right,
So
there-
if someone
there
might
are,
interrupt
there
you,
could be
you
long.
have based
It's not a lecture.
you paced the lecture for half an hour and someone interrupts you for 5 minutes, you're losing
Then
it.
you want that,
And we,
right? You don't want.
right, we don't want it like, you know,
Right.
So
so
you have to start
think-
somewhere and
right.
start and saying,
that's what we give an
okay, at
approximation,
the
usually.
end of the half hour here, everybody, do we want to hear more about this? We'll take another 10 minutes on the clock.
Right, I think what we could do is like, if we have an in-depth, like, my whole thing was I want to have two platforms. One was the basic, so people coming in that are new, well, it'll be the first thing they see, the show and tell, and then a very basic introduction to robotics. It could be Arduino, it could be, you know, something basic that we could all understand within 30 minutes. And then after that, then we do an in-depth, we'd have a break, and then do an in-depth participation like Craig. So if some people wanted to stay here and since they're really getting depth on it, they would stay. And then the other people, well, I'm not really interested in that, it's kind of over my head, they can leave and then come back. So I think that's kind of the approach I wanted, but I know we are restricted on time, like how long do people really want to be here?
Yeah, this one's, one of the
So
options, this was the most complicated. So
Oh, yeah.
it's gonna be longer, right?
Yeah, I think there's a fine pay. You had a lot of material to cover. There was no way to like do that super fast.
Yeah.
But
I would rather it be done now than break it up into 5 segments, because by the time you next month, you're gonna be like, what is the covariance matrix again? You know,
so
it's like-
we're dealing also with the real world here. So we're not a huge group, so we're a little bit taking what we can get. So I would love to do 2 presentations every meeting, and a short one and a longer one. But realistically, we don't have people to do 2 presentations
For
every
the
meeting.
few, I mean,
you
you know,
know,
Josh, I've been training them for the last 6
It's-
months easy.
And it's a volunteer group.
Yeah.
It's a free club. Criticism is relevant or relative to participation. If you're gonna criticize, come up with a solution or participate in what you think is
Change
better
the-
too.
Yeah.
So otherwise, you have to dial it in of, yeah, you gotta appreciate what you're being given.
And I think we are, and I think you're exactly right. And I love this presentation today, actually, I really geek, so. But the same token, like one time he did the studio, ML Studio, and I've seen it a ton, and it's Arduino based, and that I think was within reach for more people in some respects. But I think like the ultimate goal is like more advanced robots, so I think it's good.
Another thing we could also kind of possibly do is maybe have 2 of these type of meetings a month instead of just 1, because then we have more time to cover things. I could talk with the Science Center, I'm sure that would be possible. But I mean, would people participate at that level? Would you be interested in coming twice a month?
That'd be a little much for me. I don't know.
Right.
It's
Well, I
already
mean, we'd have
like
to, yeah, that's the thing. we
first
have to
Friday
engage.
this, and then
Right,
now
we
the
have to-
Thursday, that's 3. Now we're talking about 4.
Right,
Yeah, that's all. Because
My
you have not have, you have a lot of meetings, it's not everybody
I
spending
had to-
Exactly.
all, want to time all together
Trying to
somehow.
keep it.
Well, you could also consider when you clicked on
Build up
the
skills.
Robomo's site, you could have said, we expect this talk to be an hour and a half or whatever.
Yeah, do other
And
things.
people who aren't interested
I'm
in
trying
how
to
the
get the
talk
skills
is no
up
show.
first and find it.
Or, that would-
Yeah.
another
There you
thing
go.
too, we're talking
I mean,
about
that's what I mean.
robotics here, so
If you
it's
know
not
how
like.
long the talk's gonna be, or, you know, at least the main talk, the rest of it, you know, it doesn't matter if it goes 15 or 20 minutes. But if you say the main talk is expected to be an hour, and you know what, if you go an hour and 15 and you plan an hour talk, so what? But if you say this talk, we expect it to be 2 hours, then people who are having trouble with that are gonna just not show. And that way you have an advance notice, and you can talk to the speaker about how long he expects it to go, so it's not a lot of problem.
It's also tough to do. I mean, Craig did actually tell me, but it was the day before.
Yeah,
But I do a lot of talks. And the way I do it, I'm like, at the beginning of the month, I'm like, oh, I gotta give a talk, and I work on it a little bit over the time, and I'm not getting finished until sometimes the night before, you know, that I got the talk ready.
Sure, but you still got an idea in your head about how long you intend to make it go, and that's
Yeah.
all you want. I mean, it doesn't have to be exact.
Yeah, I knew this one, I would be having to work hard to get into an hour and a half.
Oh, yeah, and the fact is, you covered it well, and you weren't wordy, you did what you needed to do, it was an hour and a half topic, I mean, there's no question about it.
And I think
Other ones
too, is
wouldn't
like,
be.
yeah, this is robotics we're talking about, so it's not like everybody's interested, and that's another problem. Is that, I mean, Craig's talk is so in-depth, a lot of people might be just, dissuaded by coming. But I mean, it's really, the talk the lecture he gave was really a college course, a very fast introduction into slam, and it's valuable. You're not gonna get that anywhere else.
Maybe the easier thing is kind of, you already said it a little bit, but do the show and tell and the fun, easy things. It's hard to use the word fun, but the stuff that everybody gets, like right off the bat, and make a very specific time limit for that. So it's always done by this.
And I think
got,
and the reason we stopped kind of, we just like bypassed show and tell, because a lot of people bring their stuff in, and now it seems like, I mean, Nick's the only one that brought something in.
You got three.
Okay.
Two there, three, actually.
Yeah.
Well, I think
You do like the 10 to 10:30.
It's kind of,
But if we
kind of
don't,
hard to
if
do.
we don't have anything, that's,
Right.
we'll bypass it, absolutely.
Right.
See, I was moving the show and tell so open-ended. That's why I wanted to do it after the talk, where the talk's structured and the talk is really the start of the show. And then if we had time,
But if you go from simple to more advanced, when people feel they're out of their depth, they can leave.
Right.
I mean, I think that's the point here. And so,
A lot of people come for just
You
the
know,
participation, the
yeah,
social aspect
exactly.
of it. And that's why I think, like I said, the show and tell is super, I
To be honest,
I always love seeing what people
I
bring
do
in.
too. To be honest, I already did it. The first thing I did, I saw he had that on the table and I talked to him. And then the guy sitting next to me asked me a little about this. So I did show and tell a little bit.
Let me ask you a quick question, and don't, just because I gave the presentation, don't think get biased, because I'm pretty thick-skinned about that, but this is just talk. How many people want to get up and leave it, halfway through this? Anybody? I mean, so, even though it was complicated, I mean,
I wanted to see it through, but I was beginning to get concerned about, time.
yeah,
And
if
stuff.
it were a little short.
Yeah.
I think it was
This is what we're
it was
interested in
short. I
seeing.
think the presentation you did was extremely quick.
It was.
Given the
and
fact
this
that-
was a huge topic.
Right,
There were
given
other
the
topics I could
topic.
do it in 45
Right.
minutes, right, or an hour.
It was in depth enough for you to cover it. I mean, I think you did a really good job.
Yeah, but I'm saying, so this one was, I gave three options to Josh and said, and hey, everybody voted. And it's like, they picked the most complicated, in-depth one, which is okay, it's fine. It's just, I knew for the first one, it was gonna be lengthy. But if everybody wanted to stay through it, the idea that some people come and, want to look at the robots and go home might not be reality, right? That we're here we want to do that. Maybe we do the 10 to 10:30, which is always kind of fuzzy and everybody's getting organized. That's a good time for show and tell. And then 10:30 though, everybody knows the clock, like they said, the clock says 10:30. We're kicking off with a presentation to 11:30-ish, 11:30 to 12 kind of thing. Because today we got started at 10:40 talk, right? So it was an hour and 45 minutes. Other ones might be an hour, but 10:30 to 11:30 or 12 is the presentation, and then whatever we do after that.
So everybody agrees that show and tell should be first on priority?
Yeah. But I think we use that wasted time between 10 and 10:30.
While
you're all just kind of middle around.
Yeah. If you look at the Unix users group, we're structured so that we have a half hour of basic introduction or question and answer if nobody's going to do a basic session. And then after that, we do a full presentation. So from 6:37, we get the basic stuff, any little questions between the basics and the advanced. And then from 7 to 9, which is a full 2 hours, we can do whatever, ask questions. I don't think this was all out of line. It was an hour and a half. Pretty good. So I think it's maybe more time control at the beginning to start at 10 or define those time ranges. So I think
I was basing it on some other groups that I've been in that the first half hour was a social time, which a lot of groups have, because a lot of people just want to talk about, grab somebody and say, hey, I'm working on this. Have you seen this? Or I'm having problems here. It's really kind of informal and just kind of hanging out for a little bit. Maybe people don't like that unstructured format. What?
Did that mean the Thursday thing we do at your house?
Well, that would make sense more for now that we're doing the Thursday thing, but that's new.
I think it's good. That's good, but I think that informal.
That this should be our structured meeting, and Thursday should be our informal.
I really like the long and in-depth talk. It's just, I think it should be the last thing in the meeting, because then people can just, we're done. And if we're gonna have a a talk longer than an hour, we should have a break.
I agree, because then if somebody has to leave, it's easier to kind of slip out.
Yeah. Oh, we missed, not like, oh, you missed show and tell and everything else.
Yeah, then I'll miss, I write people's names down when they leave, and
That's what the video.
That's what the camera. Who disappeared?
okay, I didn't really have any club business today, which is why we didn't do club business. Nothing's really changed. I did want to bring up, I'm doing like the video recording, and I'm trying to put more content on the website. And so I've asked for content in the past, but I just wanted to point out that like it can be real simple things. Like, and if anybody's looked at robomo.club, I changed the format. Now it's more like a blog post. I think that works a little better. And so like one of our members, Lucy, I think she's like in high school or something, but she did that brain controlled robot. And I posted that up there, and the big reason I posted was laziness, because she has a Facebook page and she made YouTube videos, and to post it, all I had to do is cut and paste links from YouTube and Facebook, and I had a post that was really good. So if anybody has anything, I mean, it's so easy to use your cell phone and post to YouTube now. You know, record your robot in action, give me the link, and I'll put it on our homepage. Or if you already have a Google Plus account or Facebook or whatever thing, give me a link to it, and it gives me an easy way. I'll post your work up there so people can see. I like people seeing that we are active. We're actually doing stuff. Yeah, we're alive, because that's one of the things I think drives membership a little bit, because when I'm looking to see if I'm going to go to a group, I check out their website, and if they haven't posted in a year, I'm like, are they around? Should I even bother showing up? So anyway, I just wanted to.
There was one thing I wanted to mention. I don't know if it's still this way, because I don't remember when I got around it, but there was a question to figure out if you were a real person on the robomo.com was that, and the answer was kind of obscure. What's meaning alive? Maybe what it was, something like that. I'm like, what are you talking about? So I put it
Did you not know the answer? Okay. I thought everybody would know the answer. What's the answer to the ultimate question of life, the universe, and everything?
42.
42?
Is it 42 or 47?
42.
Yeah, I had to search for the answer.
Did you?
Yeah.
Okay.
I tried some guesses, like, I don't know, maybe that's what he wants. No, that's not it. It ended up being a hurdle. So
You don't qualify.
You don't
I
qualify.
went to first.
Yeah, that was,
I decided that was basic knowledge in our group.
Yeah, I'm sorry. It was a hurdle on that day. I don't remember if I gave up.
We have required reading.
I've only read the first 3 chapters. But,
okay.
I know what you're talking about.
I wouldn't know.
If you think about it.
So if you could make something a little more bland, maybe go back to the homepage and look for the color.
It was like putting up a sign, you have to be this nerdy to enter.
Yeah.
And you just didn't.
Let's get that class.
What do you call the thing, like, show the, like, the address thing?
Yeah,
type
it
of
does
number?
all that.
You got a free one?
I only had one.
Oh, the caption?
Caption, yeah.
Yeah.
Yeah, is that free?
Yeah.
You just throw that on there instead.
Yeah,
That might not be a
Just
bad
make it a
idea.
hurdle that's a little more universal.
Yeah, that's,
It'd be faster, but.
I never read, I didn't read Hitchhiker's Guide to the Galaxy until about 5 years ago.
I gotta read it.
The recommendation.
There was a board.
What's that first?
Look,
Yeah. They're doing it all.
But they talked to, but I mean, they picked a lot up from the hitchhikers. Sure.
That's
I
one
would
of the
like
worst
to
things
say
about
the
having
group
drive.
was going along great, so I had no complaints, but we can always be better. And,
If I come to your meetings, the Thursday workshops.
Yeah.
It probably might be the 3rd week of the month.
Okay, that's like the best week for you.
Okay, that might be the
Is that what
best
you're
week. I don't know right now, but that's like, right now what I'm seeing.
I don't have a
Because
set
I'm
thing
going-
because it's at my house, so it's kind of when I am
I'm going
available.
I'm going out at least once a week, basically on Wednesday. You know, this is on Wednesday evening, so I go over to launch program. You know, Dave's trying to learn something about job programming. You might know I'm trying to put together a webpage, basically. This is what the instructor signed us to do, and allows to basically get a job, that kind of thing, which is cool. But as I say, but I have, I don't know if you know about this, but my primary interest is robotics. I like to introduce Java development of robots. And programming of robots.
Yeah, Java's not well supported, but it can be used.
Well, either that or I could probably try Python.
Python is definitely I mean, just as far as the libraries themselves.
Okay. I thought there probably a lot, but, you know, there's a ton of self-training materials for Python out there. It's just that I gotta, in some cases, you can download and buy them.
Yeah.
Something that makes me think of is like I've been to a local grocery store
Other jobs. You know what I'm trying to do here? Yeah, that guy. Being able to touch
There's
it.
nobody who wants you to
Yeah,
We've got a 5-inch fan.
Paul said,
And raised part of the arm.
Some more on
Interaction with.
I don't know. It's hard to
That
convince
kind
them
of thing can actually touch the elbow.
Nobody wants to, and it works either way, so. I know nobody likes going out there, but no, nothing in hand, but it's still there.
Yeah, well, like, I guess I might have to still just like to figure out my customized fabric.
Yeah.